Hello. I've changed the music. I say music. I've changed the sounds. Source on the board. Today it is logic. We're moving into logic. I'm hoping that this is going to be a bit more familiar to me than set theory was, but it is a mathematical perspective on logic, not a programming perspective. Still, in theory, they should be based on the same thing. So we will see how it goes. Hopefully, well, there'll definitely be some new symbols to learn. Almost certain of that. Okay. Chapter 2, Logic. Logic is a systematic way of thinking that allows us to parse the meanings of sentences. Oh, okay, we're starting off fairly strong. Logic is a systematic way of thinking that allows us to parse the meanings of sentences. Wow. And to... hello. Thank you for your kind words. Ekshunyam. And to deduce new information from old information. That is quite a big sentence. Logic, a third time. Logic is a systematic way of thinking that allows us to parse the meanings of sentences and to deduce new information from old information. Okay. You use logic informally in everyday life and certainly also in doing mathematics. For example, say you are working with a certain circle. Let's call it circle X. And suppose you have available the following two pieces of information. Circle X has a radius of 3 units. And if any circle has radius r, the new sounds have a lot of cockerel noises on them, but I think they fade out over time. If any circle has radius r, then its area is pi r squared square units. You have no trouble putting these two facts together to get circle X has area 9 pi square units. In doing this, you're using logic to combine existing information to produce new information. Because deducing new information is central to mathematics, logic plays a fundamental role. This chapter is intended to give you sufficient mastery of it. Why did he write square units? I suppose because he's thinking about area. So he's thinking about... oh, that is a very slender circle. Let me push this up. So if this has radius, what is it? Radius 3 units. Then this will be 3. And so, and let's put a unit on this. Let's say it's centimeters, even though he's not specified centimeters. He's using an abstract unit. Then the area of this, let's say if we were to have, and this is useful as well for me. I was thinking of puzzling this out myself. Wow, pretty close actually. Pretty close. Yeah, in theory, if, you know, what is it? 9 pi. So in theory, we have 9 pi of these squares we can fit inside this, ignoring all of the bits that get cut off, etc. Or, you know, smooshing them together. 9 pi being, how much is 9 pi? Let's actually try this out. I'd be curious to try this out. 28.27. So in theory, we should be able to fit 28.27 of these in here, approximately. That's 1, 2, 3, that's 6. That's 12. I have to keep track of these. 6. Come on. 6, 6, 5. Let's go with like 3 there. And then in principle, we should have the same pattern down here, right? So we should end up with 5 roughly. I mean, let's do it. Let's just actually do this. Of course, this will be an approximation. So we end up with 3 plus 5 plus 6, 6, 5, 3. That's 28 squares there, exactly. So do we say cube unit when talking about volumes? I believe so, yes. Well, it turns out the circle formula is correct. Good, okay. It is important to realize that logic is a process of deducing information correctly, not just deducing correct information. Quite an important distinction, because in computing we can often get the correct information which we can verify, but we may not be deducing information, I suppose, correctly according to the rules of logic, or if we are, then we can't say that we are. For example, let's suppose we were mistaken and circle X actually has a radius of 4, not 3. Let's look at our same argument again. Circle X has a radius of 3 units. If any circle has a radius R, then its areas, etc. Circle X has radius 9 pi square units. The sentence circle X has a radius of 3 units is now untrue, and so is our conclusion, circle X has area 9 pi squared units. But the logic is perfectly correct. The information was combined correctly, and if some of it was false, even if some of it was false. This distinction between correct logic and correct information is significant because it is often important to follow the consequences of an incorrect assumption. Okay. Ideally, we want both our logic and our information to be correct, but the point is that they are different things. Fair enough. In proving theorems, we apply logic to information that is considered obviously true, such as any 2 points determine exactly one line, or is already known to be true, e.g. the Pythagorean theorem. If our logic is correct, then anything we deduce from such information will also be true, at least as true as the obviously true information we began with. Moving on to statements. The study of logic begins with statements. A statement is a sentence or a mathematical expression that is either definitely true or definitely false. You can think of statements... Hello, Lazy Schema, how you doing? You can think of statements as pieces of information that are either correct or incorrect. Okay. Thus, statements are pieces of information that we might apply logic to in order to produce other pieces of information, which are also statements. Here are some examples of statements. They are all true. That's very reassuring. If a circle has a radius r, then it's every even number is divisible by true. 2 is an element in the integers. Square root of 2 is not an element in the integers. The natural numbers are a subset of the integers. The set 0, 1, 2 has 3 elements. Some right triangles are isosceles. Is that always true? Just thinking. Are all right triangles isosceles? Probably no. Or are they? Is he trying to do something funny here, where some is technically correct, but not as we would say in everyday parlance? Okay, anyway, example 2.2. In fact, I'm going to look that up. Yes. All right triangles are isosceles triangles, according to answers.com, which I'm sure we can trust. So it's also true that some right triangles are isosceles, at least in this language we're building up. There's a concept in linguistics for why we would say that was sort of not we would often dispute a statement like that. I can't remember what it's called, common ground or something. No, it's something. Anyway, example 2.2. Here are some additional statements. They're all false. All right triangles are isosceles. Oh, well, I should have read ahead. Okay, that's false then. Okay. 5 equals 2. Root 2 is not an element of the real numbers. The integers are a subset of the natural numbers. It is actually quite hard to read incorrect statements. And this set is intersected with the natural numbers is the empty set, which is not true. Example 2.3, here non-statements are paired with similar statements. Not a statement. Add 5 to both sides. Yanchi Fim, hello. 3, 4, 5 triangle. Yeah, I was trying to think of a... Oh yeah, okay. If they're different, lengths, I suppose. Of course. Why couldn't I visualize that? That's so funny. Yeah. Story checks out. Adding 5 to both sides, yeah, fine. Yeah. Yeah. Yeah, fine. This is the kind of thing where, like, I mean, we will see what Richard Hammock does with this. It is Richard Hammock, right? Someone got Richard Hammond in my head. It's the thing I would criticize in curriculum where you would say, I would say, well, yes, but the learners probably don't need to be told this, but we will see. Example 2.4. We will often use the letters P, Q, R, and S to stand for specific statements. When more letters are needed, you can use subscripts. Here are more statements designated with letters. You decide which of them are true and which of them are false. Okay, for every integer n is greater than 1, the number 2n minus 1 is prime. Surely not, right? So 2... Yeah, so that would be 4, 8... And then it's well, maybe this is true actually. And we get 1, 2, 7, 63, 31. Could be. I think I remember this coming up. I remember this coming up in some way. Somehow. I remember this coming up before. Okay, 511 is not prime. And 5... Yeah, so that's not true. Yeah. So I think 229 is 512. Minus 1 is 511. And 511 is apparently is 7 by 73. So not true. Missing primes. 15 isn't prime. Oh yeah, that's more obvious. Thank you. Yeah, obviously 15 isn't prime. Wow. Okay. Humboldt. Every polynomial of degree n has at most n roots. I don't know enough about polynomials to say whether that's true or not. Degree n. The polynomial's degree is the highest exponent. So it could be true. I mean, it seems like intuitively, I guess I'm most familiar with things like this and this. These have two roots, right? These can have two roots because, yeah, they just can. I happen to know they can. This will have one root, probably. So maybe. I've never gone beyond. Could be. I don't think we need to find out, but fundamental, it's true. Fundamental theorem proven by Galois. I'll look up at the pronunciation. The function, this function is continuous. I think that's true, having tried to plot it a bunch of times. Every non-zero polynomial. Interesting. The integers is a subset of the empty set. That doesn't sound true to me. Let's go false. And this is a... This intersected with the natural numbers is the empty set. Well, that rather depends on whether you include 0. Now, this book does include 0 in the natural numbers, so this will be false according to this book, but some have disputed whether 0 is part of the natural numbers or not on this in the chat before. So, all right. So we don't get any answers to those. So, all right. Designating statements with letters, as was done above, is a very useful shorthand. In discussing a particular statement, such as the function f of x equals x squared is continuous, it is convenient to just refer to it as r to avoid having to write it or say it many times. Makes sense. Statements can contain variables. Here is an example. If an integer x is a multiple of 6, then x is even. Makes sense. This is a sentence that is true. All multiples of 6 are even, so no matter which multiple of 6 the integer x happens to be, it is even. Since the sentence P is definitely true, it is a statement. When a sentence or statement P contains a variable such as x, we sometimes denote it as px to indicate that it is saying something about x. Thus, the above statement could be denoted as px. If an integer x is a multiple of 6, then x is even. Okay. A statement or sentence involving two variables might be denoted pxy, and so on. It is quite possible for a sentence containing variables to not be a statement. Consider the following. Yes. Is this a statement? Well, it looks like a statement to me, but I guess he's saying it's not. Oh. Okay. Whether it is true or false depends on which integer x is. It is true if x is 4 and false if x is 7, etc. But without any stipulations on the value of x, it is impossible to say whether qx is true or false. Since it is neither definitely true or definitely false, qx cannot be considered a statement. A sentence such as this, whose truth depends on the value of one or more variables, is called an open sentence. The variables in an open sentence or statement, function p of x. A statement can represent any type of entity, not just numbers. Here's an open sentence where the variables are functions. RFG. Function, maybe. No, not a function. Statement R. The function f is the derivative of the function g. This open sentence is true if f of x is 2x and gx is x squared. It's false if this other case, a statement such as RFG that involves variables can be denoted either as RFG or just R. We can use the expression RFG when we want to emphasize that the sentence involves variables. We'll have more to say about open sentences later, but for now, let's return to statements. Statements are everywhere in mathematics. Any result or theorem that has been proved true is a statement that has been proved true. The quadratic formula and the Pythagorean theorem are both statements. Okay. And if a right triangle has legs of length A and B and a hypotenuse of length C, then yeah. Here is a very famous statement, so famous in fact that it has a name. It is called Fermat's last theorem, after Pierre Fermat, a 17th century French mathematician who scribbled it in the margin of a book. For all now, we know the statement. Fermat believed this statement to be true. He noted that he could prove it was true, except the book's margin was too narrow to contain his proof. It is doubtful that he really had a correct proof in mind, for after his death, many generations of brilliant mathematicians tried unsuccessfully to prove that his statement was true or false. Finally, in 1993, Andrew Wiles of Princeton University, who has come up before in our journey, as he is the reason that one of the early problems in the art of computer programming is ranked 45 difficulty rather than 50. And there's also a nice video interview with him as well, which is worth watching, announced that he had devised a proof. Wiles had worked on the problem over 7 years, and his proof runs through hundreds of pages. The moral of the story is that some true statements are not obviously true. Here is another statement famous enough to be named. It was first posed in the 18th century by German mathematician Christian Goldbach, or Goldbach, probably Goldbach, and thus is called the Goldbach conjecture. Every even integer greater than 2 is a sum of 2 prime numbers. You must agree that S is either true or false. Yeah? That seems, I guess I do have to agree that. It appears to be true because when you examine even numbers that are bigger than 2, they seem to be the sums of 2 primes. For example, all of these figures, and so on. But that's not to say there isn't some large even number that's not the sum of 2 primes. If such a number exists, then S is false. The thing is, in the over 260 years since Goldbach first proposed this problem, no one has been able to determine whether it's true or false. But since it is clearly either true or false, S is a statement. This book is about the methods that can be used to prove that S or any other statement is true or false. To prove that S is true, start with obvious statements or other statements that have been proven true, and use logic to deduce more and more complex statements until finally we obtain the statement S. Of course, some statements are more difficult to prove than others, and S appears to be notoriously difficult. We will concentrate on the statements that are easier to prove. Good. But the point is this. In proving that statements are true, we use logic to help us understand statements and to combine pieces of information to produce new pieces of information. In the next several sections, we explore some standard ways that statements can be combined to form new statements or broken down into simpler statements. Breakbeat says, these are the questions which melt my brain. Do you mean like this one? And in either case, what do you do that makes them break your brain? Are you in maths in some way? All right, we've got some exercises. Decide whether or not the following are statements. In the case of a statement, say that it is true or false if possible. Okay, great. There's an interesting sonic texture to this new sound that we're working with. There's some sort of water, there's water dripping on the microphone, I think, or something. Okay, every real number is an even integer. Well, let's come up with a notation. It is a statement, and it is false. Let's make this blue. Let's lock this as well. It's a statement and it's false because it is either true or false, I think. And it is indeed false because let's take, for example, 3.0. Every even integer is a real number. I think this is true. No, sorry, I think this is a statement. The word is doing a lot of work in statements, I think. And I think it is true. I think it's true. Every even integer is a real number because the integers are a subset of the real numbers, I think. It's a bit, I always find that statement a bit funny because in programming terms, we would consider that to be sort of not true. I mean, it sort of is, but also it's a bit tricky. So they're represented differently. If x and y are real numbers and 5x equals 5y, then x equals y. That seems like a statement to me. I don't have a very rigorous understanding of what constitutes a statement. It can be true or false. I don't think it can be in the middle. It doesn't depend on whether x or y are. Or is there No, I'm not going to overthink it. I think it's a statement. I'll find out if that's wrong. And I think, according to the mathematics I've encountered, that is true. I don't think there's anything funny that happens in multiplication that means that can be not true. Okay, that is not a statement. I think that is a statement. And I think it's true. Some sets are finite seems like a statement to me. Is and are quite important. Have we had a... So this one doesn't have is or are in it. The derivative of any polynomial of degree 5 is a polynomial of degree 6. Of any makes it a statement, I think. Now, I think, again, not having dealt with any not even dealt with really the degree of polynomials to any significant degree. Now, this should... the derivative, right? Derivative goes... I think the derivative goes down in order. So this should be false, I think. I'm going to go false. Doesn't it go the other way? Yeah. Or do you mean I can't work out if you think I'm right? Okay, you think I'm right. Yeah, I think it goes the other way. Because I think if you have like an x squared, I need to remember this stuff. But I think The derivative of this would be something lower. What actually is that? Two x. Yeah, I need to remember all those rules. I should probably just relearn all of that stuff, actually, all that calculus. I did cover it at school, but I think I basically only learned like vague heuristics, and I don't think I learned much about how it actually works. That'd be good to know at some point. Yeah, so I think the degree of this is lower. So Rook says normally propositions are introduced properly before qualification. This is doing both at the same time. Quantification. Yeah, maybe we'll find out more about that. Okay, what do we got here? We've got the natural numbers is not an element of the power set of the natural numbers. So the power set of the natural numbers would be all of the subsets of the natural numbers, which would include the set of the natural numbers. So I think that I should have this actually. I think this is true, unless there's some funny stuff about symbols. I think that's true. No, wait, it's not. It's not. It's not an element. So that's false, actually. If it was an element symbol, it would be true. Cosine x equals -1. This depends on the value of x. So I think we're saying it's not a statement, because we can't say whether it's true or false. It doesn't say like for all or anything like that. If it said for all, I think we could say it was a statement, but it doesn't say for all. It's like it's an equation, I suppose. And so it depends on the value of x. It can be both true or false depending on the value of x. I think that's what the book is trying to say anyway. All right. Real numbers productized with the natural numbers intersected with the natural numbers productized with the real numbers is the natural numbers by the natural numbers. Okay, back to the set theory. Well, they're going wild out there, aren't they, these cockerels? Okay. Now it is a statement, because there's no unknowns in there. Is it true or false? My instinct is telling me it's true, because the natural numbers are a subset of the real numbers. And so I think in this case it's true. You're not gonna work it out, but I'm going to say that's true. Number 11, the integer x is a multiple of 7, not statement. Because it has a variable in it, and I think it depends on what x is. If the integer x is a multiple of 7, then it is divisible by 7. This is a statement, right? Even though it has a variable in it, it's got an if and a then in it. So that should be true. Either x is a multiple of 7 or it is not. Statement true. Call me Ishmael. Not statement. Is this a statement? In the beginning, God created the heaven and the earth. Well, it's either true or false. So it's kind of a statement, yeah. I don't think we can say though. We don't know. Interesting. Britby Kid is saying, can you rearrange it to find X? I'm assuming you mean 9, maybe? Hmm. It doesn't fix X, though, does it? Or does it? What's cosine again? Okay, cosine X looks like this, but it's an infinite... It goes... It'll have multiple solutions at -1, right? Yeah, that's my instinct as well, Rook. 9 is not a statement since X hasn't been quantified. I suppose if there was something about... if something that made this always true, then maybe it would be a statement. Like, if we were able to say, for example, cos X equals like that, for example, like let's say if this was the thing, we could say whether that was true or false, because we know something about cosine, which means that it can never reach that number. At least according to, I mean, that seems the way it is. But for -1, where it could be or it could not be, right? Yeah. Okay, should we find out what it's an odd number, so I think in theory we get the answer to that one. So we're going to find out what Richard Hammock says, not Richard Hammond. What is happening in the audio? Something's squelching. Always a risk when you change this audio. Okay. Right, every real number is a even integer. Statement false. Oh, okay, that's a bit thick. Take that down even more. 3. If x and y, yeah, okay, so this one is a statement true. Sets, integers, and natural numbers statement true. 7 is statement false. 9 is not a statement, so that's true. Oh, it's not true, but it's, the answer is correct. 11, not a statement. 13 is a statement. For the sentence is true no matter what x is. 15, oh sorry, you can't see the answers. Where were we? In the beginning, God created the heaven and the earth. This is a statement for it is either definitely true or definitely false. There's some controversy over whether it is true or false, but no one claims that it is neither true or false. So, good. Nice. I win. I do indeed win. Wow. Good to get some practice in working out whether things are statements or not. Surprisingly challenging. Okay. Now this book is so much nicer than John Knuth's. Do you mean Concrete Mathematics, or do you mean The Art of Computer Programming? I'm going to take a look at. I think I did actually buy Concrete Mathematics at some point recently, so I will look at it at some point soon, different some point. But yeah, who knows? I mean, maybe it'll be great. Okay, and, or, and not. Now these are things that, in theory, and hopefully in practice as well, I should be able to reason about. And or not. The word and can be used to combine two statements to form a new statement. Consider, for example, the following sentence. The number 2 is even and the number 3 is odd. We recognize this as a true statement based on our ingrained understanding of the meaning of the word and. Notice that R1 is made up of two simpler statements, P and Q. These are joined together by the word and to form the more complex statement R1. The statement R1 asserts that P and Q are both true. The statement R1 is also true. Oh yeah, since both P and Q are in fact true, the statement R1 is also true. Had one or both of P and Q been false, then R1 would be false. For instance, each of the following statements is false. Yeah, we've got some false statements. From these examples, we see that any two statements P and Q can be combined to form a new statement P and Q. Okay. In the spirit of using letters to denote statements, we now introduce the special symbol, like a caret, but on the bottom of a line. Okay, great. To stand for the word and. Thus, if P and Q are statements, P and Q stands for the statement P and Q. The statement P and Q is true if both P and Q are true. Otherwise, it is false. It wouldn't go down well as an audiobook, this, would it? This is summarized in the following table called a truth table. Of course. In this table, T stands for true and F stands for false. T and F are both called truth values. Each line lists one of the four possible combinations of truth values for P and Q. The column headed by P and Q tells whether the statement P and Q is true or false in each case. Statements can also be combined using the word or. Consider the following four statements. Yeah. Now, or, we have two versions of or. So let's say, in mathematics, the assertion P or Q is always understood to mean that one or both, so it's an inclusive or, of P and Q is true. Thus, statements S1, 2, and 3 are all true, while S4 is false. The number 3 is even, or the number 2 is odd. So this is false. And this is false. The symbol V, let's call it, or, is used to stand for the word or. So if P and Q are statements, P or Q represents the statement P or Q. Here is the truth table. Fine. It is important to be aware of the meaning of or expressed in the above table differs from the way it is often used in everyday conversation. For example, suppose a university official makes the following threat. You will pay your tuition or you will be withdrawn from school. You understand that this means that either you pay your tuition or you will be withdrawn from school, but not both. In mathematics, we never use the word or in such a sense. For us, or means exactly what is stated in the table for or. Thus, P or Q being true means one or both of P and Q is true. If we ever need to express the fact that exactly one of P and Q is true, we use one of the following constructions. P or Q but not both, either P or Q, exactly one of P or Q. If the university official were a mathematician, he might have qualified his statement in one of the following ways. Pay your tuition or you will be withdrawn from school, but not both. Either you pay your tuition or you will be withdrawn from school. To conclude this section, we mention another way of obtaining New statements from old ones. Given any statement P, we can form the new statement it is not true that P. For example, we consider the following statement, the number 2 is even. This statement is true. Now change it by inserting the words, it is not true that. In this case, we get, it is not true that the number 2 is even. This new statement is false. For another example, starting with the false statement, 2 is an element of the empty set, we get the true statement, it is not true that 2 is an element of the empty set. What is happening? Somebody eating the microphone? Wow. Anyway, we use the symbol tilde to stand for the words it is not true that. So tilde P means it's not true that P. We can read P simply as not P. Unlike da 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 da, which combine two statements, the symbol... Oh, what is happening? Is something eating? Something's eating something. Just alters a single statement. Thus, its truth table has just 2 lines, one for each possible value of P. This book is from 2009. It's actually 2018. I think it was updated 2018. So it's fairly recent. The statement, I'm just going to call it not P, is called the negation of P. The negation of a specific statement can be expressed in numerous ways. Consider P, the number 2 is even. Here are several ways of expressing its negation. It's not true that the number 2 is even. It's false that the number 2 is even. The number 2 is not even. In this section, we've learned how to combine or modify statements with the operations and, or, and not. Of course, we can also apply these operations to open sentences or a mixture of open sentences and statements. For example, X is an even integer. 3 isn't, yeah. It's an open sentence. That is a combination of an open sentence and a statement. Okay, so we can build on open sentences just like statements, seemingly. Interesting. Okay. Right, so we've got some more statements to deal with. Why'd you ask, Rook? I assume it's not out of date, but if anything seems funny to you, let me know. Okay, express each statement. Oh, it appears dated. Interesting. What's dated about it, Rook? Express each statement or open sentence in a symbolic form such as P and Q, P or V, P, V, not P, in that case it'd be P or not Q, or not P, etc. Be sure also to also state what statements P and Q stand for. Okay. The number 8 is both even and a power of 2. Okay. So we could say I don't like it being up high like that. I'm going to add some little shortcuts. The explanation of exclusive or. Huh. So let's say logical and. We're going to give that this symbol. Logical or. It's going to have this symbol. We can probably deal with the normal carrot? Carrot? Deal with the normal carrot for that. Anyway, okay, so we're going to say that's better. And P is that the notation we... No, we use colons, don't we? P is the number 8 is even. I should probably find a way to make this a little easier in the screen. Let's just go with this. Q is the number 8 is a power of 2. Okay. Whoa. Whoa, I'm really having trouble with my board today. Okay, 2. The matrix A is not invertible. I think that's... Oh yeah, no, it'd be a complement, right? Or, what do they call it? Negation? Yeah, negation. I already sort of, like, for me, made the connection. These sort of map a little bit across to, like, at least my temptation is to map them across to union, intersection, and complement in set theory, where union would be or, even though my brain wants to tell me it's intersection. Intersection would be and complement would be negation. So Rook's saying the modern explanation for exclusive or would be A or B and complement A and B. Yeah, that makes sense. Maybe we'll get to XOR. So I guess XOR might not come up a lot here. Thank you, Bambicapello, for the sub. I appreciate it. Okay, 2. The matrix A is not invertible, so we're going with negate P. Does seem to have a space in this notation, where P is matrix A is invertible. Okay, 3. X is not equal to Y, or we could say that. Well, we could just use regular old statements here, probably. Does it want us to put it in some other way? I don't know. I don't know what it's expecting there exactly. But I think I could just put it like this, right? And then for this one, I suppose we could simplify it. We could break it down a little bit, and we could say P or Q, where P is Y is greater than X, and Q is Y is equal to X. We could do that. It doesn't seem necessary, but we could do. 6. There is a quiz scheduled for Wednesday or Friday. Well, I'm tempted to say this, where but I don't know if we need to be clever about saying that it's not going to be scheduled. Well, at least in English, we would say that we would need to exclude the or here to properly represent it. Yeah, we need to make it an exclusive or, because I suppose if a teacher said to me there is a quiz scheduled for Wednesday or Friday, I wouldn't assume it to be on both days. So, I mean, if we were going to, but maybe we should interpret it as a mathematical or anyway. In any case, if we wanted to, let's say if we wanted to fully qualify it, we'd say as you said in the chat, Rook, and we'd have, I guess we want maybe some, I don't know what the behavior of these things are yet, and then we'd have this. So if we wanted to exclude both, we'd need to do that, but I don't know if we do. 7. The number x equals 0, but the number y does not. So in this case, let's start off with the statements. Number x, or the question, open sentences, I guess these are open sentences. The number x equals 0. Yeah, so we've got these two sentences here, and we could then say P and complement Q. Sorry, not complement, not Q, negation Q. At least one of the numbers x and y equals 0. Right. So in this case, we can put this as x equals 0, and q can be y equals 0. And then we can say P or Q, and this would be in symbolic form, I think, or gate. It's very thrilling, this musical, this backing track today. Okay, 9. The element x is an element of A minus B. Huh. I guess he wants us to put this in a different form. If we were to try to break this down, again, I'm not exactly sure what he's expecting here, but let's say we have the statement x is an element in A, and then Q can be x as an element in B. Now what is this? Can we put this in logic terms rather than set terms? So that set A minus B is going to be all the elements of A that are not in B. So we're going to say that if this is true, then P has to be true, and has to not be in B. So negate Q. Quite interesting. Because if it's, so the reason for this is it has to be in A to be an element of A minus B. And it has to not be in B, because if it was in B, it would be removed from this A minus B set. Okay, now we've got X is an element of A union B. In this case, we're going to be able to say, let's take these statements again. Now union is going to be an OR, because it's going to be in either of these if it's going to be an A union B. And then for 11 looks considerably more annoying. Okay. We're saying here that A is an element of a set, and this set is the x's in the power set of the natural numbers where the cardinality of the cardinality of the complement of x is less than infinity. The cardinality of the complement of x, and x is going to be a subset of the natural numbers. So let's say if we had, oh, okay, that's not right. Wow, that noise really grates on me. Okay, so one element in the power set of the natural numbers might be that. Now, if we had this, the cardinality of its complement, which would be all the natural numbers not in this, would be infinite. So let's say if we had, let's use a better letter, let's say G. The G with a hat on, which I'm going to have to use this to do. Come now. Yeah, the cardinality of this I need a better way to say complement without getting into LaTeX, sorry. Yeah, cardinality of this is going to be infinite. So do we need to work this out, or can we shortcut it in some way? We might not need to work it out properly. What would our statement be? A is an element in this set. Well, actually, we probably do need to work it out. So let's say the cardinality of this is infinite, right? And no matter what numbers we choose for our x, no matter what set we choose for our x, which will be a subset of the natural numbers, I believe the cardinality of the complement is always going to be infinite. No matter how many numbers we add to a subset, to construct a subset of the natural numbers, we are going to have an infinite number of numbers that are not in that set, unless we have all of them. I guess if we have all of them, if we have the natural numbers as our x, then the cardinality of the complement of the natural numbers, presumably within its universal set of the natural numbers, is going to be the empty set. So its cardinality is going to be less than infinite. So this set is going to end up being just the natural numbers again. And then the question is A an element of the natural numbers? Or is that, I need to work out it's actually going to be, is A an element in a set which contains just one element, which is the natural number, which is the set of natural numbers. So actually I think this set is going to look like this. We get an answer to this one, thankfully. I don't know how much of this work is necessary. So, I mean, I think there's only one statement here anyway. So I think it's probably just going to be P. And then presumably this reduces to something interesting, but I don't know exactly what it would be, other than my best guess is, so it's something like that maybe, but I'm not 100% sure. Have I taken a class on Prusufor from Odebasi? No. Is it obvious? Hopefully it's obvious. That's the best I got for 11. We're going to find out. Happy families are all alike, but each unhappy family is unhappy in its own way. Okay, so we've got to put this in symbolic form. Thanks, Odebasi. Nice username. Happy families are all alike. Okay, let's say that but is really doing an and job there, isn't it? Each unhappy family is unhappy in its own way. Yeah, that but isn't really it's not doing any negation there. The sound, I'm going to lose my mind at this sound. 13. Human beings want to be good, but not too good and not all the time. This exercise, I'm grading this exercise a fail. This is not this is not good. Okay. Human beings are not all the time. I think that's I'm going to call those ands again. If he has anything different, I'm going to send him on a literature course. I've rage baited myself with this sound. I'm going to say that's and again. I think it's and again. I think it's and again. How you doing, by the way, Chiara? Lazy Schemer says, I read problem 12 as starting with type families. Oh. Yeah, maybe there's a whole nother scheme here. All right, let's end this horrible section. Let's see what deranged answers these questions have. Right, 1. P and Q. I will take that. 2, we don't know. 3. Yeah, fine. 5. I mean, whatever. No. Wrong. But kind of right. 7. P. Yeah, that's right. 9. Yeah. 11. 11, who knows what he wanted there? He just wanted it restated, I guess. Or no. No, wait, this is the answer, right? A is a subset of the natural numbers, or... No, wait. And the cardinality of the complement of whatever set we're talking about is less than infinity. Okay, fine. I'll take the L there. 13. You're just wrong. You're just wrong there. You're just incorrect, Richard Hammock. I'm sorry. I'm right. He's wrong. He needs to read harder. Sorry, Richard. Oof, that's really gotten me, that has. Okay. Oh my god, the sound. What is going on? Okay, I'm changing it. I'm changing the sound. And AI is attempting to tell me my business streaming as well. Okay. Oh, it's still going. I just skipped ahead like half an hour. Are you done? Okay, all right. Hopefully Wow, that was rough. Oof. Okay. Yeah. So this question, right? Human beings want to be good, but not too good, and not all the time. Let's look. Let's just examine. Let's examine this a bit further. I can still hear it. I can still hear that noise. Where are we? Here we are. Okay. So, yeah, here we are. Let's look at this. Human beings want to be good. Okay, great. Wait, yeah. Human beings want to be good. Great. We can say that's P, right? And, fine. The comma but is an and, great. But not too good. And what he's saying here is not humans want to be too good. Human beings want to be too good. But that is not really what this means, right? It means humans want to be like, maybe I'm convincing myself it's right now. But not too good. I think that is making an affirmative statement that humans want to be good, but not too good. You know, they want to be a certain level of good. So I don't think it's negation, because I just don't think it is. And not all the time. Human beings, and so he's negating human beings want to be good all the time. I guess that is kind of correct. I don't like it. I don't like it. I don't like it. It's not right. Richard, that's just not it. Sorry, Richard. Backpack, hello. I find it's quite the interesting feeling as I continue to learn new things, and some symbols end up having dozens of different meanings depending on the context. How resourceful we are at repurposing the buttons on the keyboard. Indeed. What we really need is to bring back, we need to bring back the APL keyboard, which I think was probably designed for a lot of these situations. What did they have? They had all kinds of wild stuff on that keyboard. Yeah, they had there was a programming language called APL, which was somewhat popular when in the early Unix days, let's say the Multics days, and some people still use it, of course. And they had a keyboard which had all of this on it, which would be pretty handy. This so Tommy asked, which volume is this of the art computer programming? So it's not. We're on a side quest at the moment, learning about proofs. So it's no volume. But thanks for asking. Yes, the art of computer programming starts with a lot of, well, it starts with some proof stuff. So I want to understand the proof so I could understand that chapter better, or at least not be so bewildered going forwards. Anyway. Curious. We got a this symbol here. What do you think that means? And we've got a divide symbol up here too. We've got a multiply and a divide as distinct from the X. That's quite nice, isn't it? Wouldn't hate this. Wouldn't hate having this right now. I suppose I could set up a keyboard layout that had that. I could just buy probably you can get keycaps that have this on. That'd be pretty cool. Project idea. Okay, all right. I'm cooling off. Not so angry about George Orwell quotes now. Not so angry about the sound. Nice sound, nice bird sound. I tell you, the last backing audio made it for like 4 weeks. This one, it's it's kind of nice. It's nice in a way, but that scratching sound. Okay, all right. Oof. What is that? It's like a listening party. What is that? Okay, hopefully it doesn't come back. What kind of algorithm is my favorite? Asked Tommy Rex. You know, I never even considered that question before. Well, that's really hard. Sound off in the chat if you have a favorite algorithm. I tell you what one I don't like. I don't like doing A star routing, if that's how you even say that out loud. I don't like doing that. I always forget that one, how to do that one. I've gotten to the point now where I can sort of remember it for Advent of Code challenges, but I've you know, I get bits wrong all the time. I don't like binary sort or binary yeah, don't like binary search. That's what I mean. Don't like that. That annoys me. I think I shouldn't be in computing. I don't like shunting yard. Nah, screw shunting yard. No, well, don't like that. I don't like the well ordering algorithm because it's not an algorithm. I'm just hating now. I think I like quicksort. Quicksort's pretty good. Quicksort's kind of pleasing. I don't think I could implement it straight off, but it's quite pleasing. Quicksort. Backpack says, I was very proud of myself yesterday for making a nice, neat recursive function, and I used it to replace a nasty branching algorithm that's broken. That's great. That's a great feeling. Yeah, I once watched a talk by Dan Abramov, who he had a whole thing that he did. He did a whole scheme, which was like clearly part of his whole internal method, where he replaced it. He had this method of refactoring imperative code, like stateful imperative code, which was horrible to work with, into pure functions, and it was wonderful to watch. He's quite an opinionated person, so it's hard to agree with him on everything he says, but that was quite special. I got him in to talk to a bunch of beginners to programming. I think they understood almost nothing he was saying, but I loved it. So it's great for me. Hopefully it stuck with some of them. Okay, where are we at? Conditional statements. There is yet another way to combine two statements. Suppose we have in mind a specific integer a. Consider the following statement about a. If the integer a is a multiple of 6, then a is divisible by 2. We've got a then in there. We immediately spot this as a true statement based on our knowledge of integers and the meanings of the words if and then. If integer a, alpha, is a multiple of 6, then alpha is 7. So therefore alpha is divisible by 2. Notice that R is built up from two simpler statements. Yeah. In general, given any two statements P and Q whatsoever, we can form the new statement if P then Q. This is written symbolically like P, I guess I would call this a fat arrow in JavaScript. P then Q, which we read as if P then Q, or P implies Q. Like and or, the symbol arrow, let's say then, has a very specific meaning. When we assert that the statement P, if P then Q is true, we mean that if P is true, then Q must also be true. In other words, we mean that the condition P being true forces Q to be true. A statement of form P, if P then Q is a conditional statement because it means Q will be true under the condition that P is true. Think of if P then Q as a promise that whenever P is Q, Q will be true also. There is only one way this promise can be broken, i.e. be false, namely if P is true but Q is false. So the truth table for the promise P, if P then Q is as follows. So if both are true, then true. If this is true and this is false, then it's false. If this is false and this is true, it's true. Okay, fine. So it's kind of asymmetrical, I suppose. That's how it seems to me. Perhaps you're bothered by how if P then Q is true in the last two lines. I'm not bothered. I'm not bothered at all. Here is an example to explain it. Suppose your professor makes this promise. If you pass the final exam, then you will pass the course. Your professor is making the promise. You pass the exam. If you pass the exam, then you pass the course. Under what circumstances did she lie? There are 4 possible scenarios, depending on whether or not you pass the exam and whether or not you pass the course. These scenarios are tallied in the following table. So you might pass the exam, and you might not pass the exam and then pass the course. This is the one I guess he's concerned about. The first row is the scenario in which you pass the exam and you pass the course. Clearly, the professor kept her promise. So in the T, in the third column, indicates she told the truth. In the second row, you passed the exam but failed the course. In this case, your professor broke her promise. And the F in the third, yeah. The third row describes the scenario in which you failed the exam, but you still passed the course. How could that happen? Maybe your professor felt sorry for you, but that doesn't make her a liar. Her only promise was that if you passed the exam, then you would pass the course. Yeah. She did not say passing the exam was the only way to pass the course. Since she didn't lie, then she told the truth. So there is a T in the third column. Finally, look at the fourth row. You failed the exam and you failed the course. Your professor certainly did not lie to you, hence the T in the third column. If this month is September, so for another example, consider this statement. If this month is September, then there is an equinox in this month. An equinox is a day for which there are equal hours of darkness and light. There are 2 equinoxes per year, one in September and the other in March. The above statement is thus unquestionably true, for it asserts correctly that if the current month is September, then an equinox will occur this month. In symbolic form, the statement is true, but the open sentences, this month is September and there is an equinox in this month, are either true or false, depending on which month it is. But if P then Q is always true. This is shown below for 3 out of 12 months. Notice how if P then Q is true, even when P is false. Yes. If P then true is a true statement under this particular example, there's no month in which P is true and Q is false, unless we imagine that the Earth is destroyed by an asteroid before September 21st, a possibility that we shall not entertain. I was once told that if there is a good test, I once read this actually, there's a good test for working out if you should have a joke in your curriculum. And it is, if you, upon reading the joke the third time, is it still funny to you? And I think this doesn't pass the test. In mathematics, whenever we encounter the construction if P then Q, it means exactly what the truth table for if then expresses. Of course, there are other grammatical constructions that also mean if P then Q. Here is a summary of the main ones. The meaning of each is encapsulated by the table for if then. P implies Q, if P then Q, Q if P, Q whenever P, Q provided that P, whenever P, then also Q. P is sufficient condition for Q. For Q, it is sufficient that P. Okay, that's a slightly more unusual one. Okay, Q is a necessary condition for P. For P, it is necessary that Q, P only if Q. Okay. These can then be used in the place of and mean exactly the same thing as if P then Q. You should analyze the meaning of each one and convince yourself that it captures the meaning of if P then Q. For example, if P then Q means the condition of P being true is enough, i.e. sufficient to make Q true, hence P is a sufficient condition for Q. That is the, says Rook, that is the law of detachment. If P implies Q and P then Q. Thank you for the vocabulary. I mean that, by the way. Sometimes I sound sarcastic, but I do mean that. Vocabulary is important. Okay. The wording can be tricky. An everyday situation may help clarify it. For example, consider your professor's promise. This means that your passing the exam is a sufficient, though perhaps not necessary, condition for you passing the course. Thus, your professor might just as well have phrased her promise in one of the following ways. Passing the exam is a sufficient condition for passing the course. For you to pass the course, it is sufficient that you pass the exam. However, when we want to say if P then Q in everyday conversation, we do not normally express this as etc. But such constructions are not uncommon in mathematics. To understand why they make sense, notice that if P then Q being true means that it is impossible that P is true but Q is false. In order for P to be true, it is necessary that Q is true. Hence, yeah. Different ways of saying the same thing. Okay. Jara says the jokes and general whimsy in certain parts of Gödel, Escher, Bach are always amusing. Go Hofstadter. Yeah, I need to read that at some point. It's a book, right? Oh, they're kicking off out there. It's like a sort of playful mathematical book. Cool. Okay. We got some exercises which I will attempt to skip through. Come on. There we go. Without changing their meanings, convert each of the following sentences into a sentence having if P then Q. These sounds. Differentiable. Wow, really can't spell these things. Integrable. Wow, is that how you say that? Integrable? Huh, there we go. I hope he's not going to sneak any sort of not applicable ones in. He probably will. 3 is tripping me. All right, let me think about this a bit more. For a function to be continuous, it is necessary that it is integrable. I didn't actually put that in any of these. For a function to be continuous, it is necessary that it is integrable. If a function is integrable, then it is continuous. That's not right. That one's wrong. I think this actually should be phrased as no, wait, I'm getting this wrong again. If a function is... No, it is right. If a function is integrable. Wow, I should have paid more attention in the earlier chapter, shouldn't I? If a function is integrable, no, wait. If a function is continuous, then it is integrable, right? It's not the other way around. A function could be integrable but not contiguous. Continuous, sorry. I think. Okay, if a function, right, a function is rational if it is a polynomial. Yeah, fine. An integer is divisible by 5 only if it is divisible by 4. No, wait. Oh, okay. Harder than I expected. Let me slow down. An integer is divisible by 8 only if it is divisible by 4. So if a function is... if an integer is divisible by 8... Okay, whenever a surface has only one side, it is non-orientable. If a surface has only one side, then it is non-orientable. A series converges whenever it converges absolutely. If a series converges absolutely, then it converges, I think. 8. A geometric series with ratio r converges if the cardinality, I guess, I don't know if that's cardinality still. If cardinality of r is less than 1. Probably it means something different in this context. It's probably not set theory at that point, maybe. Okay. In any case, we don't need to know. If bar r bar is less than 1, for a given geometric series, then it converges, I think. A function is integrable, provided the function is continuous. The discriminant is negative only if the quadratic equation has no real solutions. If has no real solutions. You fail only if you stop writing. Stay out of the literature, Richard. You fail only if you stop writing. Okay. Absolute value of R, of course. Of course. Yeah, I should have something about ratio here. How do I phrase this properly? I don't know. If for a given geometric series with ratio R, then it gets something like that. Oh, there's even more. Oh no. People will generally accept facts as truth only if the facts agree with what they already believe. Edgy. Then they will accept those facts as truth. 13. Whenever people agree with me, I feel I must be wrong. I made a typing mistake with number 10. Thank you. Beaver Logic 2. Great username. If a quadratic equation has no real solutions, then, oh yeah, I did, didn't I? Then, oh yeah. Okay, all right, let's find out. How much left have we got of this logic? Logic's really making me angry. Oh my gosh, there's so much. Okay. Okay. It just goes on. Wow. Okay, let's hope it gets harder or less annoying or something. Okay. Yeah, thereabouts. Oh, I got 3 right in the end. Great. 5. Great. 7. A series converges when it converges absolutely. If a series converges absolutely, then it converges. Great. 9. If a function is continuous, then it is integrable. Yep, fine. 11. If you fail, then you stop writing. Oh, I got that one wrong. Okay, we'll go back to that one. If people agree with me, then if it's okay, that one's fine. All right. So 11. You fail only if you stop writing. Oh, okay. Yeah. So this one should actually be. If you fail, then you have stopped writing. Yeah, so, yeah. That only if. There's a sort of consequential movement there. Okay, worth keeping an eye on. All right. All right, let's look at this. Biconditional statements. Only if it implies. Okay. Biconditional statements. It is important to understand that P if P then Q is not the same as if Q then P. To see why, suppose that A is some integer and consider the statements A is a multiple of 6. If A is a multiple of 6, then A is divisible by 2. If A is divisible by 2, then A is a multiple of 6. The first statement asserts that if A is a multiple of 6, then A is divisible by 2. This is clearly true. Yeah, I get the idea. The conditional statement of Q, if Q then P, is called the converse of P if P then Q. So a conditional statement and its converse express entirely different things. But sometimes, if P and Q are just the right statements, it can happen that if P then Q and if Q then P are both necessarily true. For example, consider the statements A is even and A is divisible by 2, A is divisible by 2 and A is even. No matter what value A has, both of these statements are true. Since both if P then Q and if Q then P are true, it follows that these OR are true also. Let's introduce a new symbol, this symbol here, double arrow, to express the meaning of the statement, this biconditional thing here. The expression, how do we read this? How would we pronounce that? Anyway, if P double arrow Q is understood to have exactly the same meaning, according to the previous section, if Q then P is read as P if Q. Right, okay. According to the previous section, Q arrow P is read as P if Q, and P arrow Q can be read as P only if Q. Therefore, we pronounce P double arrow Q is as P if and only if Q. Fine. Right, okay, so what he's saying here is this means, this can be pronounced as P if Q, and this could be pronounced as P only if Q. Therefore, we can pronounce this P if and, with this and here being. Okay, so he's trying to expand this in some way. He's like, you can pronounce this as, well, you can pronounce this as if, and this as only if, but the other way around. Fine, you get P if and only if Q. Fine, which is like, some people use that with two Fs, so like a double F if, I think. Hello, Harmony Hype. It is not the proof book by Jay Cummings. It is the proof book by Richard Hammack, or Hammock. Have you read the other one? Is it good? Thanks for the link, Yara. How many pages am I in? I am 47 pages in. Okay. We've got this. We've got this. We've got another truth table. So if both are true, then true. If true and false, false. If false and true, false. If false and false, true. Okay, great. Compare the statement R with this truth table. Not surprisingly, there are many ways of saying if and only if in English. The following constructions all mean P if and only FQ. It is that way round, isn't it? Yeah, it is. Well, it doesn't matter, I suppose. Necessary and sufficient. Necessary and sufficient. Equivalent to. Equivalent to, interesting. And conversely. Okay, fine. How many have passed? How many hours did it take me to get here? I don't know. Probably. I would guess we're currently kind of getting up to maybe 20 hours. Terrible going, honestly. But I am streaming at the same time, so. Yeah, pretty slow. You could definitely work through faster. The first three of these are just combined constructions from the previous section to express, etc. Beaver logic asks, the equivalent to implies logical equivalence. There can be equivalence relations where they don't imply each other. Maybe. It's a good question. Yeah, somebody who knows maths can respond. Yeah. Put it in the chat if you know the answer to that. Okay. Without changing their meanings, convert each of the following sentences into a sentence having the form P if and only if Q. For matrix A to be invertible, it is necessary and sufficient that whatever that thing is. We don't need to worry about order this time. So let's say if and only if. No, wait. Matrix A is invertible if and only if the determinant, I guess, determinant of A is not equal to 0. If a function has a constant derivative, then it is linear, and conversely. A function has a constant derivative if and only if it is linear. If xy equals 0, then x equals 0 or y equals 0, and conversely. So we can say xy equals 0. Xy is 0 if and only if x is 0 or y is 0. Yeah. If alpha is an element of the what's the word for that? Quotient? It stands for quotient, right? What does that symbol mean again? Rational numbers? Rational numbers. If alpha is in the rational numbers, then 5 alpha... Actually, that's not alpha. If A is in the rational numbers, then 5A is in the rational numbers. And if 5A is in the rational numbers, then A is in the rational numbers. Okay, so we're saying A is in the rational numbers if and only if 5A is in the rational numbers. For an occurrence to become an adventure, it is necessary and sufficient for one to recount it. I think that's from the novel Nausea by Jean-Paul Sartre. For an occurrence to become an adventure, an occurrence becomes an adventure if and only if one recounts it. Interesting. Okay, we'll leave it at that. Truth tables for statements. We should now know these truth tables. They should be internalized as well as memorized. You must understand the symbols thoroughly, for we will now combine them to form more complex statements. For example, suppose we want to convey that one or the other of P and Q is true, but they are not both true. No single symbol expresses this, but we could combine them like this. Yeah. This statement will be true or false depending on the truth values of P and Q. In fact, we can make a truth table for the entire statement. Begin as usual by listing the possible true/false values of combinations, true-false combinations of P and Q on 4 lines. Yeah, we get the idea. You're putting a table together. The helper columns. Yeah. Making a truth table for these entails a line. Fine. We fill in the 4th column. Yes. This colon has some meaning. Did I skip where that was introduced? Is it like given, maybe? Probably given. Okay. I'm just skipping through this because it's not very interesting, I don't think. The moral of this example is that people can lie, but true mathematical statements never lie. That is a moral I can take without reading the scenario, I think. We close this section with a word about the use of parentheses. The symbol negate is analogous to the minus sign in algebra. It negates the expression it precedes. Okay, fine. So it's sticky. Okay, fine. Okay, we'll make us some tables. Yeah, let's do it. Let's make some tables. I think I'm going to do the odd ones this time. Just enough to just check that I'm not making any, not just misunderstanding things. Okay, true, false, false 2, true, false, true, false, true, false, true, false. Wow, okay. Now, if we're going to have Q, R, if Q then R, how to express this in this table? I'm actually not 100% sure. This way you do the exercises, folks. Okay, if Q then R, what's the truth table for that? Get this in my brain. Right, so this statement is going to be true in the situation where, in all situations except this one, except where it doesn't follow that if Q is true, then R is true. I think the level of evaluation we're doing is a little tricky to me. Okay, so in this case, this will be true, this will be false. This will be true, this will be true, this will be true, this will be false, this will be true, and this will be true. Then we've got, wait, what's the thing we're working on here? Yeah, this one. Okay, this is this thing. And this is like PV. Which means, and this is OR, right? So it's OR of these two. So that's going to be true. Wow, I need better colors here. Let's make this this. Let's not do that. Let's bring this here. It's these two columns we care about. Okay, true or false is true. True or true is true. True or true is true. False or true is true. False or false is false. True. True. Okay, so that's going to be our truth table, I think. Okay, let's move on from that and let's skip this one and do 3. I will definitely find out if I've misunderstood this stuff later on. Now in this one we've got this, oh, okay, got this statement here. We only need Q's here. And that means we also only need every other of these rows. Thankfully. Okay, so if we want those, then we're going to have true here. If P, then Q. That's false. That's true, and that's true. And then the final result is going to be the negation of that. So true, sorry, false, true, false, false. And then this is going to be the negation of it. Okay, 5. 5, we've got this delightful thing. So we've got 2 variables, thankfully. We don't have to put together a huge table. I think I'm actually just going to make a little helper version of this. Except I'm going to put it in blue. Let's make this a bit bigger. Oof, okay. Nope. There we go. There are some pigeons in the audio now. I'm quite pleased about that. Okay, so we've got P. We want to have negation P. We could put that together, I suppose, but let's just try and do it a bit faster than that. If it's P, what the hell? What on earth is this? P or... No, P and negation P. Well, that's always going to be false, right? That will be true and false, so that's false. This will be true and... Oh no, it will be true sometimes. No way, I'm looking at it wrong. It's actually going to be... yeah, it's always going to be false. It's always going to be fine. Actually, just fool myself into thinking the wrong thing. Yeah, so P and negation P is always going to be false. And then we've got or Q. False or Q. So it's just going to be Q. That's going to be the same as Q, right? I think. Okay, let's try 7. Yeah, so we've got a slightly more interesting one here. Am I losing my mind? Surely P and negation P is going to be always false, right? If false, then Q. If false, then so it should always be the same as... All right, let me get my brain around this again. If it's false, if the first element is false, then it doesn't matter what the second... If the first statement is false, for if then, it doesn't matter what the second statement is, right? So it should be true always, I think. Well, we're going to find out. Okay, 9. Okay, what are we doing here? We're taking the negation of P, which is going to be false, false, true, true. And we're taking the negation of Q as well, which is going to be false, true, false, true. And then we are we're ORing them. False, true, true, true. And then we're negating that, which means we're going to get true, false, false, false. Okay, number 10. No, we're not. Well, let's do number 10. It looks kind of interesting. Suppose the statement P and Q or R, if that's true, then R or S is false. Find the truth value of P, Q, R, and S. This can be done without a truth table. Can it? I'm sure it could be. Okay, let's work backwards on this. So if it's false, yeah, if it's false, then we can say, yeah, if we look at the truth table for if then we can say that there's only one situation in which this is false, and it is when this is true and this is false. So we know that R or S is false, and we know that P and Q is true. So we know these things. Now, we've got the or here. Now, if this statement is false, then both of these have to be false. So we can say that R is false, S is false, and given that, we can also say, let's actually break this up a bit here. Given that, we can also say that's going to be false, this is going to be or, so that means this is true, which means that P and Q are also going to be true. I'm vaguely following along with the chat, and my eye got caught on the if then. This this symbol is the devil, dude. It's like a meta operator. Wow, it's evil, but it looks so happy, don't you think? Maybe that's why it's the devil. Okay, I think that's let's say 10 is right. Let's move on to 11. Okay, suppose P is false and that the statement if R then S, if and only if P or Q is true. Find the truth values of R and S. This can be done without a truth table. Okay, fine. So we know that P is false. And then we've got R and S. And these are equivalent. It's actually and. These are equivalent. So we're saying that these are equivalent, and the truth table for that statement will be true if both are true and both are false. Both are true or both are false. Or rather, this is true if and only if this is true. This is true if and only if this is true. And also, this is true only if and only if this is true. Or rather, this is true if this is true, and this is true if this is true. So we're saying that both are true, right? Let's go with that and see where it takes us. I'm going to look back at the truth table at the end for if and only if. Okay, so if P and Q is true, then we can say P is true and Q is, well, actually we know P is false. Sorry, this is an and, right? Yeah. Well, we know P is false, so I've got something wrong there. Let me look back at the truth table for this. No, I was right about the truth table. This if and only if symbol. Do we call them operators here? I don't even know if we call them operators in this context. Symbol. Yeah, so either they're both true or they're both false. And we know that P and Q cannot be true because P is false. So we're going to say they're both false. In which case, in which case, if P is false, yeah, so this whole expression will be false. This means that they must both be false, which means P is false. Oh my gosh, okay. What if P is false and both are false? In the condition where both sides of this double arrow are going to be false and also P is false, then Q must be true because we need P and Q to be false. And so they have to be different. No, they don't. Let me get this in my brain again. P I should really know this better than I do. So in this case, true, false, false, false. So the situations in which P is false and the whole expression is false could be one of these three things. No, one of these two things. It could either be true or false. So Q is not bound to anything yet. We don't know what Q is. But we do know this is false. Okay. We don't need to know what Q is. We've not been asked to find Q. So we've got this. Now what if R then S? We know if R then S is going to be false. So if this can be true, that's false, this is true, and this is true. So if this whole thing's going to be false, we know this is the only row this can be. And so R has to be, sorry, this is going to be, We know that if this whole expression is false, then R has to be true and S has to be false. Okay. Whew. All right. Those were quite fun, those last ones. All right, let's find out. Let's find out how wrong I am. How much my skimming hurt me. What have we got? Need to change the sounds. Need to change the sounds. Okay. Did I put them in the right order compared to what they were expecting? No. Oh, no, I did. I did. Oh, thankfully. In which case my answers should be correct. T, 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 T. T, F, T, T. Okay, I think I've got that one right. Vinto, yes. Hammock's book, yes, indeed. Correct. 3. Write a truth table for this. False, true, false, false. Great. 5. True, false, true, false. Great. 7. All truths. Oh, that's correct. 11. Right. R is true and S is false. Wow, I got that right. Amazing. Great. Wow. Impressed. Impressed myself. Okay. Logical equivalence. All right, I'm going to take a short break. I'm going to change the music, change the audio in that time. Probably back in about 5 minutes. So I will see you on my return. Actually, I'm kind of enjoying this sound now. Something scurrying around. Anyway, enjoy the scurrying. I won't change it just yet. I've returned. Hello, Happy Nora. Now I have to find some better noise. I have to not accidentally upload something. Upload some of the other random sounds on my computer. There are far too many treacherous noises. Five in a row. Yeah. Go Happy Nora. Thank you for tuning in. 5 in a row. Okay. Whoa. Okay. Sorry for the sudden immediate rainfall. Aggressive rainfall. Headphone warning. Post warning. So you ever had those days on Twitch? I mean, I'm someone who, I don't know if all. Wow, that is quite loud actually. Let me turn my. It's okay, maybe you can turn it. You can turn it down. So you have those days on Twitch sometimes when you tune into, because I engage in Twitch. I watch Twitch. I don't know if this is common for streamers, but I do. But I enjoy it. And sometimes you tune in, and you choose a bunch of channels, and it's like I call it hell Twitch. Like you've just tuned in to people like experiencing, just having a terrible time. Just like, and you're just watching someone just not enjoy themselves for hours, and you're like, why am I why am I doing this? And I feel like I'm really giving that today. I'm giving hell Twitch today, where I'm paying for some terrible deeds I did in a well, probably not too terrible. Some mildly bad deeds, like maybe in another life I learned to drive, and I wouldn't let people merge in ahead of me or something. And so now this is my penance. It's rough going this part. Oof. Okay. Yeah. But it's all right. It's good. I'm going to bring a positive attitude. Got my iced coffee. I've allowed myself a sit down. I'm sitting down now. I don't know if you can tell. And we're gonna look at logical equivalence. Backpack Vacuum says logic is useful but not always enjoyable, and all horses have legs. That is a true statement. Wait, let's put that. Write that down. How do we express that? Oh, I've got like the worst possible theme on. I've decided, by the way, I'm making my own whiteboard. I'm doing it. It's gonna be great, and you know what? It's gonna have transparency. I think. I guess you could say that, right? All right. We already did this section. We did this. We did this already. We did this. Wait, did we? No, we didn't. Oh, I was just about to skip some logic. Oh, that'll be a shame. In contemplating the truth table for P if and only if Q, you probably noticed that P if and only if Q is true exactly when P and Q are both true or both false. In other words, P if and only if Q is true precisely when at least one of the statements P or Q or no, sorry, P and Q or not P and not Q is true. This may tempt us to say that P if and only if Q means the same thing as P and Q or not P and not Q. To see if this is really so, we can write truth tables for P if and only if Q and this other thing. In doing this, it is more efficient to put these two statements into the same table as follows. This table has helper columns for the intermediate expressions. Yeah. So we have this expression here and this expression here, and they are the same. Wow, I was really hoping that would be like a twist or something. This table shows they have the same truth value no matter the values for P and Q. It is as if these are algebraic expressions that are equal no matter what is plugged into variables P and Q. We express this state of affairs by writing, etc. Hi to Brazil. Mesa Verde. Hi to Brazil as well. From the UK. Something Brazilian came up today in my life. I can't remember what it was. And in saying that these are logically equivalent, in general, two statements are logically equivalent if their truth values match up line for line in a truth table. Logical equivalence is important because it can give us different and potentially useful ways of looking at the same thing. As an example, the following table shows, yeah. The fact that if P then Q, or Q if P, is equal to this expression is useful because so many theorems have the form if P then Q. As we will see in chapter 5, proving such a theorem may be easier if we express it in the logically equivalent form negate Q, if negate Q then negate P. Two pairs of logically equivalent statements in particular are significant enough to have a special name. De Morgan's laws. Fact 2.1. We're only on the first fact. We haven't had any other facts in this chapter so far. Okay, De Morgan's laws. Negate P and Q is equal to the negation of P or the negation of Q. Negate P or Q is equal to the negation of P and the negation of Q. Okay, pleasing. It's verified by using the following table. The first one is verified. We already had De Morgan's laws for sets. I guess we did, although they didn't get called that in the book. The first of De Morgan's laws is verified using the following table. You're asked to verify the second one in one of the exercises. Fine. De Morgan's laws are actually very natural and intuitive. Consider the statement. Yeah, it's not the case that both P and Q are true. If it's not the case that both P and Q are true, then at least one of P or Q is false, in which case, yeah. De Morgan's laws can be very useful. Suppose we happen to know that some statement of form negate P or Q is true. The second of De Morgan's laws tells us that negate P and negate Q is also true. Hence, negate P and negate Q are both true as well. Quickly obtaining this additional information could be extremely useful. Here is a summary of some significant logical equivalences Those that are not immediately obvious can be verified with truth tables. Okay, we've got some laws here. Let's go through the laws. The contrapositive law indicates that if we have a if P then Q, then we also have if negate P then negate Q then negate P, so they're swapped. So in this case, if we're saying, let's say if the sky is blue, then it is daytime. We can say if it is not. Wait, so let's put this properly. Yeah, so negate Q. If it is not daytime, then the sky is not blue. Is that true? Am I getting that wrong? I'm getting it right, apparently. Chat says I'm getting it right. Maybe I just chose a weird example. Because you're right, Law Sayer, it could be. It's not necessarily... Well, I guess this is actually true of our reality, right? If it is not daytime, so it's night, then the sky is not blue. I guess that... Wow, I'm really struggling with basic reality today. Okay. 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 All right. De Morgan's laws. So in this case, yeah, I guess, well, Backpack, you're totally right. The sky isn't blue. Although it does appear blue sometimes. Okay. So let's say we've got... Yeah, we've kind of already gone through that. We don't need to go through that one again. De Morgan's laws, we've just gone through. Commutative laws. P and Q equals Q and P. Fine. Distributive laws. We talked about it a little bit last time based on a conversation in chat, so I have a better understanding of that now. P and Q or R is equivalent to P and Q or P and R. And then we've got P or Q and R is equivalent to P or Q and P or R. Okay, fine. And then associative laws. Right, so we don't need to use brackets to share these out, I guess. That's kind of what this means. Okay. Notice how the distributive law has the same structure as the distributive law from algebra. Yeah. Concerning the associative laws, the fact that this thing is true means that the position of the parentheses is irrelevant. And we can write this as P and Q and R without ambiguity. Similarly, we may drop the parentheses in an expression such as, yeah. But parentheses are essential when there is a mix of these, as with this. Indeed, yeah, these are not logically equivalent. Okay, great. Okay. We'll do the odd numbers of these. Just to get some practice in. Flush out any misconceptions? Okay. So let's try and do these in a reasonably quick way. And in fact, I should make this a little easier to deal with. Okay, so if we're going to have P if we're going to have this, then we're going to say Q or R and P. That's true. That's true. That's true. That's false. False, 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 false because of the and. Okay, and then let's look at another one. Let's look at, so this is supposed to be P and Q or P and R. Okay, so in this case we've got P and Q both true, or so P and Q, where P and Q are true, we can just take that as true. So let's say that's true, that's true, don't know, don't know, don't know, don't know. Yeah, so we know those are true. Then for these, we need to look at the second group, P and R. True, P and R are true. P and R are not true. P and R 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 not true. Okay. Equivalent. Let's look at number 2. No, sorry, number 3. Now for this one, which is this one, I don't want to do that. We've got, let's say P, Q. So if P then Q, which is only false if R is Q is false and R and P is true. So true, true, false, false, true, 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 true. And then for negate P, sorry, negate P or, yeah, we want to make this red. Negate P or Q. So negate P, F, or, yeah, so when negate P is true, we can have that be true. So that would be, we don't know, we don't know, don't know, true, 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 true. And then here, it's where Q is true, 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 sorry, true, true, false, false. Okay, equivalent. P implies Q. So Hans says P implies Q equals not P or Q. What does the equals operator stand for? Equivalence. Yes, logical equivalence, I think, is what is attempted to be said here. That symbol, Happy Nora, is that another way of saying negation? I feel like I've seen that symbol around. Logical negation. I guess they're using the tilde in here, in this book, but maybe elsewhere it's, or maybe they mean different things. But okay, 3. That's 3. Yeah, they're using the tilde symbol. I don't know why. Okay, 5. We've got these 3 here. So this one, yeah, so this is the negation of the or over all of these elements. All of these statements, I guess. So let's first find the non-negated version. And then we negate it, which will be everything but the last one. Okay, and then for this one, we've got these. Now this is the and. Yeah, the and over the negation of each one. And I think I've been clever enough to put these in the other order than they need to be, so I can just work from the bottom and over that. But it's not quite adding up. So negation of this, negation of this, negation of this, and then the and of that is going to be false. Negation of this, the and of that is going to be false. Yeah, I mean, we know if they're not all the same and they're not all true. Yeah, fine. Okay, let's look at number 7. Right, so we've only got 2 columns here. So here we're going to have P, if P then Q, and we actually don't need half of these as well. Should have just copied it from earlier. So this one's true, this one's false. Oops, doing it in the wrong text. True, false, true, true. And then we're going to have oof, what a weird expression. Let's break this down a bit. So let's say we've got this, and then we're going to have to also get Q and negation Q. And then with the thing. Okay, let's take a look at this. Now, P and negation Q. So that's true and false, which is false. That's true and true, which is true. That's false and false, which is false. That's false and true, which is false. Now Q and negation Q is always going to be false, right? It's supposed to be on this one. And then this is true. This is false. It's true and true. Huh. So they do. What a weird equivalence. Still, I'm sure it'll be useful. Maybe is it one of the ones we're given? No, it's just he's just maybe combining a few. Okay, we won't do 8. And then we'll move on to B. Okay, B. B9. Are they equivalent? P and Q and not P or not Q. Okay, well we could use truth tables for this, so we could try to express them in a different way. I wonder which way will be better to do. Let's take a look at these laws. What do we got we can use? Equivalence, a commutative law. We've got this type of thing. This law does indicate this, right? Because if we've got P, I've made the text really small again. If we've got P, Q and Q, let's say we've got this. Let's say we got this. Now, let's say we negate both sides. Is this a way through? And then we negate this. And that's the law, right? That's the law. That's the law. So the law says so. So it is. Anything to avoid using a truth table. All right, 11. So we've got this type of thing. And what can we do with this? We've got the contrapositive law. Looks a little bit related, maybe. Not dramatically so. Doesn't look directly substitutable. Probably one we could use a truth table for this one. Yum, you've made the understandable error of assuming I've set up any commands in the chat. But I imagine you might be wondering what we're doing. We're working through the Book of Proof by Richard Hammock. Okay, so we've got 11, we've got P. I'm going to delete that. So let's pull out P, if P then Q. Which is going to be true, false, true, true. And then let's try to take this. So this is going to be negation of P and this. So that's going to be false and true, which is false. That's going to be false and false, which is false. That's going to be true and true, which is true. And that's going to be true and true, which is true. Okay. And then if we try to take Q and P, and then we'll negate that in place. So Q and P is going to be true here, false here, and true here. Kind of tricky to read. And then we're going to negate this to get this. And then we see that they are not seemingly equivalent. So let's go with no, not equivalent. Okay. I'm not sure how to tell whether that's true or I'm just working it through again, so I'll move on. We'll find out later. 13. Now we've got these are true by the associative laws, right? PQR, PQR. And then we don't have a 14, but let's do 14 just because it's the last one. Okay, now for here we've got P and... Oh no, wait a minute here. I got tripped up. He tripped me up. Not true, because these are different symbols. Different operations. Sorry, that's bottom of my screen. That's this one. Let's work on this a bit. Can we do anything funny with these laws at all? Doesn't seem so. I guess we're just doing it. Shouldn't be too difficult. Okay. Let's start with Q and R. True, false, false, false. True, false, false, false. And then if we want to have a P... Come on. There we go. So this is going to be P or. So true, 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 true. True, false, false, false. Tucker Zenith, hello. You're following from YouTube. Thanks for the series. Thanks for tuning in. Hope you're enjoying it. Hope you're enjoying it more than I am today. Okay, and then the other way around. We're going to go with P or Q. That's going to be true, 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 false, true, 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 false. And then this, but the other way around. So that's going to be that one and R. So let me just make sure I don't read this wrong. We're going to be looking interested in this one. And this one as well. And we're interested in the situation where both are true. True, false, true, false, true. Getting the true, false ASMR. False, false. All right, they look pretty unequivalent to me. Not equivalent. Oh, okay. Zoomed out too far. All right. Okay, I'm bored with this. Let's look at the answers. See if we can juice out anything. Correct one. Hey, it might be worth using the distributive law. So I think... Oh, yeah. Wait, that is right. Yeah. True. I was looking at the wrong law. Let's look at that one again. Okay. So we've got this. Oh, no, we got this. Second one down. So it doesn't look like they're equivalent because we've got this P in here, or at least not, I mean, not, they don't evaluate to the same expression. So I think no, also by the distributive law, I think. So not equivalent. Let's find out. All right. 2.6, number 1. True, true, true. And then the rest are false. That's correct. 3. 3, I've done something super weird for some reason. Did I just do the wrong one? I guess I just did the wrong one. I don't know what I'm doing there. Let me look at that one again. 5. All false except for the last row, which is true. True, false, true, 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 false, true, true. Then B9. Yes, equivalent by De Morgan's law. 11. Not equivalent. We did that by truth table, so I guess we made the right call there. And they're not equivalent as well. He doesn't say exactly how he computed it, but still. Okay, so what was I doing with number 3? Was I just on the wrong one? Probably. It's definitely the... definitely the most obvious. So yeah, I was just doing something wrong. I was just on the wrong one. For some reason. Oh no, I was just... I just didn't mark it. I just had a irrelevant R in there for no reason. Did I get the answer right? Yes, I did, although I did it in a weird way. So I got doubles of everything, but the answer's right. Okay, logical equivalence. All right, moving on. Quantifiers. Using the symbols we have seen so far, we can deconstruct many English sentences into a symbolic form. As we have seen, this symbolic form can help us understand the logical structure of sentences and how different sentences may actually have the same meaning as in logical equivalence. But these symbols alone are not powerful enough to capture the full meaning of every statement. To see why, imagine that we are dealing with an infinite set of integers. Suppose we want to express the statement every element of x is odd. We would have to write this thing here where px is the open sentence, x is odd. And if we wanted to express there is at least one element of x that is odd, we'd have to write this thing. The problem is that these expressions trail on forever. To overcome this defect, we will introduce two new symbols. We saw these before when we were spooling ahead. Two new symbols, upside down A and reverse E. The symbol upside down A stands for the phrase for all, and the reverse E stands for there exists. Thus, the statement every element of x is odd is written symbolically as for all x is an element of for all x elements in x, px, and there is at least okay, wait, what is going on here? It's supposed to be something that, or is this just, oh, right, so we've previously defined this x is odd. Okay, fine. Fine. P stands for predicate. Maybe. There is at least one element of x that is odd is written succinctly as reverse E x for all x in x, px. These new symbols are called quantifiers. The symbols upside down A, I do like those. I do like upside down A and reverse E. Are called quantifiers. Upside down A stands for the phrase for all, for every, for each. Reverse E stands for the phrase there exists a, or there is a. Thus, the statement for every n in the integers, 2n is even, can be expressed in either of the following ways. You know, such and such. Yeah, for all and for some is a nice, more symmetric way of putting it, isn't it? Thanks, Rook. Likewise, a statement such as there exists a subset x of n of within the natural numbers, I guess, for which the absolute value of x, or no, the cardinality of x is 5, can be translated as this horrendous set of symbols. There exists an x such that x is a subset of the natural numbers and the cardinality of x is 5. Or there exists an x, a set x, which is a subset of the natural numbers where the cardinality of x is 5, or there exists an x which is an element of the power set of the natural numbers where the cardinality of x is 5. We love saying things in the same way. Chickens are really getting to me today. The symbols, I'll call them A and E, are called quantifiers because they refer in some sense to the quantity, all or some, of the variable that follows them. The symbol A is called the universal quantifier and E is called the existential quantifier. Wow, that's quite a troubling phrase, isn't it? Existential quantifier. Statements containing them are called quantified statements. A statement beginning with upside down A is called a universally quantified statement, and one beginning with reverse E is called an existentially quantified statement. The following English statements are paired with their translations into a symbolic form. Every integer that is not odd is even. For all n's in the integers, we can... So if the negation of n is odd is true, then the statement n is even is true. Okay, there is an integer that is not even. There exists some n in the integers where the statement, and n is not even holds to be true. Or something. Yeah, makes sense. And makes sense. Well, it's going to be pretty useful to put this feel pretty good to put this notation to use at some point. Given a set, I do mean that sincerely as well. A quantified statement of form, because this seems pretty impenetrable. I can feel that things like this to me, like a few weeks ago, would be like, "What on earth are you talking about, bro?" But I can just about pick them apart now, which is good. More powers, new powers to read Knuth's books with. Are there any new facts in here? A quantified statement is understood to be true if px is true for every. If there is at least one, yeah, this will become useful with proofs, right? We just need to find one counterexample. Here are some examples of quantified statements that are false. Every integer is even. Yeah. For every real number x, there is a real number y for which y squared is equal to x. Oh yeah, I think that is false, right? The news is currently blowing up in the UK. Just don't even, I'm not even going to read it. Okay. Two rational numbers, A and B, yeah. Whatever. Examples. When a statement contains two quantifiers, you must be very alert to their order, for reversing the order can change the meaning. Consider the following statement from example 2.5. For all, I guess this is the whole thing. For all x's in the real numbers, every y, sorry, not every, there exists a y in the real numbers where y cubed is equal to x. This statement is true, for no matter what number x is, there exists a number y equals cube root of x for which y cubed is x. Now reverse the order of the quantifiers to get a new statement. There exists a y in the real numbers where for all the x's in the real numbers, y cubed equals x. This new statement says that there exists a particular number y with the property that y cubed equals x for every real number x. Right, okay. So in this one, we've got no matter what number x is, there exists a number, yeah, where this is true. Whereas here we're saying there exists a y for which for every x in the real numbers, y cubed equals x, yeah, which is clearly not true. Or, seems not true. Since no number y can have this property, that the statement is false. The two statements above have entirely different meanings. Quantified statements are often misused in casual conversation. Maybe you've heard someone say, all students do not pay full tuition, when they mean not all students pay full tuition. While the mistake is perhaps marginally forgivable in casual conversation, it must never be made in a mathematical context. Do not say all integers are not even, because that means that there are no even integers. Instead, say not all integers are even. Wow, what a... Who hasn't heard of the magic y that can be turned into any real number by cubing it? That would be pretty good. I would like to meet that number someday. Okay. Yeah. You can hear the rain. The funny thing, it's not even raining here. It's my magic sound bed to cover up the incessant noise of all of my chickens that exist in my room. All of my hundreds of chickens that I keep living in my room. I can't quite drown them out with all of this artificial rain noise. They keep making a racket. Just making myself laugh now. Okay, but it is true. There are several hundred chickens. When they have barn eggs, by the way, in the UK, this is what they mean. They just mean my flat. Okay. Write the following as English sentences. Say whether they are true or false. We'll do this. We'll do this. Wait, I can just zoom in. That's false, right? Because we could have 0. X could be 0. Nickedoodle777 says, I wonder why mathematicians took symbolism so far as to make the perpetuity of decoding notation syntax, and why it's so short, like programming makes intuitive sense, but these shorthands feel contrived, like expecting to read assembly as intuitive as C or as English. Yeah, really interesting question. Anyone got any takes in the chat on why mathematical symbolism is like this? Why do this? I'll just add there was a time where like they were trying to make programming languages look like this. In fact, one of the big reasons we don't program like this is really COBOL. It's really Grace Hopper's work. Not entirely, but certainly some people thought that programming language should look like this in the olden days. I say the olden days, in the 60s, let's say. But they didn't win. Didn't win the argument. Yeah, it would be a tough time for keyboard manufacturing if they did win. Okay, 3. There exists a number in the real numbers where for all numbers in the real numbers, ax would equal x. a real number which, let's say a real number alpha or a, for which every real number can satisfy ax equals x, something like that. A real number x, let's say. There exists a real number a for which every real number x can satisfy this. I think this is true because a could be 0, right? No, wait. That's not true. Be 1. A could be 1, and then that would be true. There exists a real number a for which every real number x can satisfy. Yeah. So if a was 1, then every real number would be this. Yeah. So I think yes. Oh, there's an a for each x. Maybe I have this wrong. Yeah, I guess that would be another way of putting it. Yeah, so another way would be that the reason I'm stumbling over that one is my English brain is saying that this might allow a different a for each x. But a mathematician would probably be more precise about that, I suppose. Okay, 5. For all the n's in the natural numbers, there exists a set x in a subset. Well, we can shorten this even further. A subset of the natural numbers where the cardinality of that subset is less than n. So we could put this as there exists a subset x of the natural numbers of cardinality less than n. Okay, is this true? So for every natural number n, there exists a subset x of the natural numbers of cardinality less than n. So, well, this is going to be true for like a number like 5, let's say. So we could have like 1, 2, 3, 4. If n was 5. And it would exist for 1 because we could have the empty set as a subset of the natural numbers. But it wouldn't exist if we had 0 in the natural numbers, right? So it would be false. Okay, let's move on to 7. So 7. For all subsets, for all subsets of the natural numbers called x, there exists an integer where the cardinality of that subset is that integer. And this seems straightforwardly false. So let's frame this. Oh, maybe it is true. For all the subsets of the natural numbers, which could include the empty set, the set with 0 in it, the set with 5 and 6, 7 in it, etc. So the cardinality is always going to be 0 or more. There exists an integer where the cardinality of this subset is going to be, yeah. So the cardinality of, basically, the cardinality of a set is always going to be an integer. Is always going to be in integers. You can't have like fractional or, I mean, you can't have negative, but it doesn't really matter in this case. So I think it's true because I mean, I don't actually know if this is true. Maybe there's some weird cases where it's not. Yeah. The chat is saying maybe about this one. If I remember correctly, the book assumes that 0 is not in the natural numbers. No, it assumes it is in the natural numbers in this book. For every set X, and Rook's saying for every set X contained in N. Hmm. And Happy Noor is saying N is a subset of N. Oh, that's true. Okay, for all subsets X are the natural numbers, so this could be the natural numbers. There exists an integer where the cardinality of X, which in that case would be infinity, is N. Are we allowed to have infinity in the integers? I don't actually know. What do we think? I suppose if you think about it, like the natural numbers are infinite in size, but they don't contain any number that we could describe as infinity, right? Or rather, it's same with the integers, right? Yeah. So we could have this be n. We could have this be the natural. We could have x be the natural numbers, the set of natural numbers. In which case, the cardinality of x would be infinite. But I think we don't have infinity in the integers, so we can say that this is false. I'm convinced. They're infinite subsets. That's true. Although the cardinality of all the non-infinite subsets, which might also be anyway. We'll find out. Okay, 9. 9. For all the n's in the integers, there exists an m in the integers where m equals n plus 5. That seems oddly simple. True, I guess. And then we're given a slightly different one afterwards, which we'll do just for fun. Okay, for, let's say there exists an m, an integer m, where all every integer satisfies m equals n plus 5. I think false. Nicodol says, doesn't a subset demand a cardinality, or is an infinite subset incardinal? If every subset has a cardinality, there should be a number in the integers to represent it. There are infinite subsets, but a particular subset X has a cardinality. So I think the case that that I think makes that tricky is one of the subsets of the natural numbers is also going to be the set of natural numbers. So we're also going to have an n. And so what's the cardinality of n of the natural numbers? Well, it's infinite. It has, you know, it doesn't have a cardinality we could write down. And then the question is whatever the cardinality of the natural numbers is whatever the cardinality of the natural numbers is in the integers? And I think probably the answer is no, but I guess it probably depends how you define the integers. Like, is that are we allowed to have infinite values in this? I don't know. Yeah, there's a magical m that's always just 5 steps away from any other integer. Yeah. That would be a nice number. Starting to like some of these imaginary numbers, you know. Okay, let's find out. Some of these are pretty interesting. Let's find out what Richard Hammack says. Let's get the marking pen out. Okay, statement is false because of 0. 3. Statement is true where a is 1. Statement is... Ooh, I got that one wrong. Okay, for every natural number n, there is a subset x of n. For every natural number n, there exists a subset x of the natural numbers of cardinality less than n. Oh no, you're totally right, actually. Happy Nora, you said this earlier. Why did I just invert reality? The book assumes 0 is not in the natural numbers. You're right. I don't know why I just decided it did. I just not just forgot. But I didn't I did more than forget. I just affirmatively believed the opposite. Yeah. It's really Ren. Hello, how you doing? How you doing? Good to see you. Okay, well, 5 corrected. 7, right. So the book says false for the reasons we discussed, with thanks to chat for the hint on this. For example, the set X of all even natural numbers, for example, is infinite. Oh, it's gotten rainy again, hasn't it? I'm glad you're doing well. It's really Ren. I am well too. We're working through logic, and it has been a little more tedious than set theory, but we're getting to some good bits. 9, true. Okay, great. Okay, more on conditional statements. No, no. No, please, no. Have you had to reverse logical statements yet? Kind of. We'd have to do some negating. We have to do a lot of rephrasing. Yeah, we've had negations. We had a bunch of negations. We've got a bunch of this going on. All this stuff. It just goes on. Just goes on. The bit that really gave me the rage was we had a bunch of we had this human being. We had to put this in logical terms, which I got wrong, and then got angry about. So. Okay. Have you done inverse with logical quantifiers, like how the inverse of for all is there exists? No, actually, haven't done those yet. Though maybe we will get onto those soon. Okay, more on conditional statements. And before we do, is taking the cardinality of an infinite set even a valid operation? I don't know what set the cardinality of sets is in, actually. Does anyone know? What is the set of the cardinality of sets? Oh, okay. Hamak says, it's time to address a very important point. In this case, about conditional statements. Oh, I know what's happening. Getting some... there we go, that's better. To motivate this, let's return to the following example concerning integers. X is a multiple of 6. If x is a multiple of 6, x is even. As noted earlier, every multiple of 6 is even. This is a true statement no matter what integer x is. We could even underscore this fact by writing the true statement as for all. But now, to switch things around to get the different statement. This is true for some values of x, such as... oh yeah, okay. So this is the... We've swapped it around. But false for others. Thus, we do not have a statement, but rather an open sentence. However, by putting a universal quantifier in front, we get for all x in the integers. If x is even, then x is a multiple of 6, which is definitely false. So this new expression is a statement, not an open sentence. In general, given any two open sentences, px and qx, about integers x, the expression for all x in the integers, if px, then qx is either true or false. So it is a statement, not an open sentence. Now we come to the very important point. In mathematics, whenever px and qx are open sentences concerning elements x in some set x, depending on the context, An expression of the form if px then qx is understood to be the statement for all x in x if px then qx. Right. So there's an implied for all there. In other words, if a conditional statement is not explicitly quantified, then there is an implied universal quantifier in front of it. This is done because statements of the form for all x in x are so common in mathematics that we would get tired of putting for all x in x in front of them. Thus, the following sentence is a true statement, as it is true for all x. If x is a multiple of 6, then x is even. Likewise, the next sentence is a false statement, as it is not true for all x. If x is even, then x is a multiple of 6. This leads to the following significant interpretation of a conditional statement, which is more general than but consistent with its definition in section 2.3. If P and Q are statements or open sentences, then if P, then Q is a statement. This statement is true if it's impossible for P to be true while Q is false. It is false if there is at least one instance in which P is true but Q is false. Okay. Thus, the following are true statements. Yeah. Okay. Happy Nora says, not making this up, I promise. The numbers you use for measuring cardinality are called cardinal numbers. The smallest infinite cardinal number is Aleph 0. I think that's hopefully that's how you pronounce that. Fascinating. Wow. There you go. How about that? Thrilling stuff. The behavior of cardinalities of infinite sets is more complex. For example, there exists a bijection, word I don't know, between the set of all natural numbers and the set of all rational numbers, Q, and thus the cardinality of n is the cardinality of Q, even though n is natural numbers is a proper subset of the rational numbers. Something that cannot happen with proper subsets of finite sets. However, a fundamental theorem due to George Cantor shows that it's possible for two infinite sets to have different cardinalities. In particular, the cardinality of the set of real numbers is greater than the cardinality of the natural numbers. The cardinality of the natural numbers is usually denoted by this Aleph null, since it's the smallest Aleph number. Cardinality is studied for its own sake as part of set theory, and is used in a bunch of other contexts as well. Huh. There you go. Imagine being the smallest infinity. Oh, just so embarrassing. Embarrassing. Terrible. Always looking up to all the other infinities. So sad. Not all infinities are equal, yeah. That I had heard of. How interesting. Okay. Translating... Oh, no, wait. I skipped... Did I skip? No, I didn't. Translating English to symbolic logic. In writing and reading proofs of theorems, we must always be alert to the logical structure and meanings of the sentences. Sometimes it is necessary or helpful to pass them into expressions involving logic symbols. This may be done mentally or on scratch paper or occasionally even explicitly within the body of a proof. The purpose of this section is to give you sufficient practice in translating English sentences into symbolic form so that you can better understand their logical structure. Here are some examples. Consider the mean value theorem from calculus. If f is continuous on the interval ab and is differentiable on ab, okay, so that's a closed interval at first and then open interval second. Then there's a number c in the open interval AB for which f quote c, yeah, it's calculus. Use a translation to symbolic form. You need the big brackets. Break out the big brackets. For every... No, there exists a C in the interval AB for which this equation holds. Oh, derivative, of course. Derivative. Derivatives. Consider Goldbach's conjecture from section 2.1. Every even integer greater than 2 is the sum of 2 primes. This can be translated in the following ways, where p is the set of prime numbers and x is the even numbers. Even integers greater than 2. If n is in X, then there exists a P and a Q in the prime numbers. Or is that notation? Maybe that notation means something different. No, there exists a P and a Q in the prime numbers such that n is equal to those two numbers added together. Fine. And or, probably or, and in another way, for all n's in X, there exists a P and a Q. Oh, X is the even numbers. For all the n's in the even numbers, there exists a P and a Q in the prime numbers for which n equals P and Q. Okay, fine. P add Q. These translations of Goldbach's conjecture illustrate an important point. The first has the basic structure such and such, and the second has structure this one. Yet they have essentially the same meaning. This is significant. Every universally quantified statement can be expressed as a conditional statement. Every universally quantified statement, that's something like this, can be expressed as a conditional statement. Right. Interesting. So everything of this form with a for all on the front can be expressed as an if then. Or implies, I guess. Suppose that X is a set and QX is a statement about X for each X in the set X. For each element in X, the following statements mean the same thing. Yeah, it's just what we're talking about. This fact is significant because so many theorems have the form of a conditional statement. The mean value theorem is an example. In proving a theorem, we have to think carefully about what it says. Sometimes a theorem will be expressed as a universally quantified statement, but it will be more convenient to think of it as a conditional statement. Understanding the above fact allows us to switch between the two forms. Great. The section closes with some final points. In translating a statement, be attentive to its intended meaning. Don't jump into, for example, automatically replacing every and with this and or with this. For example, at least one of the integers x and y is even. Don't be led astray by the presence of the word and. The meaning of that statement is that one or both of the numbers is even, so it should be translated with or, not and. Like this. Finally, the logical meaning of but can be captured by and. Yeah, as we've seen before. The sentence, the integer x is even, but the integer y is odd, is translated as. Yeah. And then we got some exercises. Whoa, okay, just spooling straight on. How much more we got of logic to do? 11. Oh, we're almost to counting. Finally. I'm going to be able to get to count. I'm going to be able to count soon. We're going to I think we're going to finish logic today, you know. I'm not leaving logic for one more session. Absolutely not. I've had enough of logic. I intend to live illogically from this point on. Okay. Right. Oh, he's decided to be literary again. Oh dear. All right, let's do this. Okay, if f is a polynomial and its degree is greater than 2, then the derivative of f is not constant. I don't know how to do this. I mean, I get like it's going to have this structure, right? But what goes in here? We could do this. We could do that. Probably there's some way you want to notate this, though. Yeah. Q says something like this. Oh yeah. Okay. Yeah, I guess that would work. That'd be a nice way to put it. Pleasing. So this kind of replaces like P and Q, right? What am I doing here? Oh, it is and. It's kind of like that. Neat. Come on. Okay, 3. If x is prime, then root x is not a rational number. If p, then I don't have my root anywhere. Let's go with this. Is not. Did I make this? No. This is in the Q, isn't it? That's the Q symbol. Okay. For every positive number epsilon, see, I know that one. Epsilon, there is a positive number. I was feeling so excited. Delta. Delta. Oh. Delta, for which the absolute value of x minus alpha a is less than delta implies, oh my gosh, the absolute value of f of x minus f of a is less than epsilon. Okay. So we're going to have I haven't made my symbols yet. They've done their little font. They really have just turned the A upside down. Okay. For every positive number, this will be in the natural numbers, I think, in this case. Or did they, I can't remember which. Did they say 0 counts? No, they said 0 doesn't count. So that's fine. There is a positive number. Oh, no. We didn't say positive integer. So we might say I guess we default to the real numbers. So maybe I suppose we're assuming that 0 is not positive, or maybe something like that. There is a positive number. Gosh, awkward. Then we want the backwards E. Do we have that there? Nope. Come on. Get out of here, backwards E. There we go. There is a positive number delta. What a mess. I'm just going to put it like this. I feel like this is nicer. There is a positive number delta. There exists a positive number delta again in this context for which What even is the... Did I miss an important part of the syntax here? No. It's just a comma separated list for which ugh, it just goes on. I guess that's the answer. That's the strict definition of limits in calculus. Huh. Maybe Knuth will force me to spend some time in calculus at some point. 7. There exists a real number A for which... Yeah, okay. There exists a real number A for which for every real number x not loving this notation at the moment. Let me go back, see if I missed some dots or something. No, it really is just commas everywhere. Makes me feel uneasy. Okay. It's really Ren is interested if I've tried LaTeX. I've used LaTeX in the past in previous study. I don't think it's not. I have found it quite useful for doing work privately, but not very good for displaying work. But this isn't that good for displaying work either. Like as in, because it's all, code. It's all in. It's a kind of code. It to me, it's not the right tool for it, but I will try it. Though I've taken a look at it and I wasn't convinced, but I'll give it a go. If x is a rational number and x is not 0, then tan x is not a rational number. We could write it like this. I'd really like to get a graphics tablet. That would probably be the right choice. Oh no, it's not rational. It's quotient. I think that's it's not real. It's rational. Rational is Q, right? 9 can be used to show the irrationality of pi. Yeah, Epic Man, you're right. Rational numbers Q, not R. I guess I could do 8. I don't eat anything that has a face. This is equivalent to I eat everything that doesn't have a face, right? There'd be a way to put this. Something like a for all things that don't have things that have a face. I don't eat them. Something like that. So it could be so let's go with R. A. Maybe. Maybe this. For all x's in for all things in the set of things that have a face. I don't eat. I don't eat them. Or I eat them, I think. No, they are not equivalent. Chat is saying I'm wrong. Chat is not convinced. Okay, so this, or we know this is I eat Q. Then this is going to be I don't. Well, not I eat Q. Is that the same as that? And then we're saying for every thing that has a face, I don't eat. For every Q that has a face, I don't eat Q. There's no X in things I eat and things with faces. Oh, that's an interesting way of putting it. There's maths, computer science beef in the chat. This is prerequisite study. This is all preparatory work to getting to the art of computer programming by Donald Knuth, which we will get to, I promise. You just got to hang around for a long while. So this is all programming, really. No, it's not really, but it's it's on the route. You know how games devs, they have their whole maths thing that they do? Imagine this like that, but for programming. Okay, they're saying I'm wrong on number 8. We'll never know. Well, we will know. We will know. Put your expressions for number 8 in the chat. I'm curious, actually. Is there any way to be good at computer science by not learning maths? Probably not by. I mean, I've done a bit too much logic today. Probably not by not learning maths. Like, not learning maths will not consequently get you to being good at computer science. But there is a way to be good at making software without learning any maths, for sure, or without learning very much maths. It's definitely not a requirement to be able to build software, even by hand. And of course, AIs make that considerably easier these days. But it was always true. I mean, hence the fact I've been in the software industry for sort of one way or another. Some of that actually building production software for a fair while, knowing less maths than I knew until I started this project. Yeah, but computer science, as Stephen is saying, computer science, probably you'd need to know a decent chunk of maths to be good at computer science specifically, which is not entirely the same thing as building software. In fact, there probably is there's like a, to go back to our Venn diagrams, there is a sort of probably this between computer science and building software, I think. But none of this is necessary. If any of you had the idea that any of this work I'm doing is necessary for anything other than doing this, you are sadly mistaken. None of this is necessary. As somebody put, I think in the first stream that I did on the art of computer programming, or actually it was a YouTube comment, AI could one-shot all of this. AI could one-shot all of this. It's true. Probably a lot of the maths. I mean, almost certainly all of the maths I've done, and AI could one-shot all of it. But I would like to retain. I would like to develop my capability. Is why I'm doing this. I think one reason I'm doing this. There's a province that protects. I'm just not into the verbal ones. There is a providence that protects idiots, drunkards, children, and the United States of America. Otto von Bismarck. Okay, so I think this one is like. Maybe you could probably say he means something. He probably there's an implicit spread operator in there, but maybe there's not. Maybe it's only as a class. And then you could say there's the backwards E, right? Maybe. There exists. Let's go, I don't know, a providence. There exists a Y. Maybe there's a 4. Maybe there's a 4 all in there. Probably there's an implied for all. For all x, there exists a providence that protects. Maybe something like this. Maybe like something like that. Lawsayer says, I recall they tested Claude on the Tower of Hanoi. Pronunciation may be, and it failed for n is greater than 5. Kip says, I'm not convinced by the artificial intelligence. Maybe if one does not have their own, artificial is fine. Adeka says, yeah, you're doing it for the fun of it. If AI can do it, then what will I do? Nothing remains to be fulfilled. Yeah, I sort of feel like I had a little idea a way back talking to a friend where, now, like many people, not all people, don't really have to use our physical strength very much to perform our jobs. And partly because of this, we go to the gym in order to strengthen our bodies and to, in some extent, to some extent, going to the gym is basically kind of pointless. I mean, it has points, but there's no point outside of ourselves for doing that. Like, there's no useful work performed at the gym other than that it improves our bodies, maybe our lifespan, our other things that we might do in our lives, but they're fundamentally work on ourselves. And as more labor leaves the sphere of human beings and enters the sphere of automation, maybe we will be relying much more on a mental kind of gym, a kind of brain gym but not in a cringe Nintendo DS type way, but as a genuine. We will need to keep ourselves sharp. I think, like, people are already talking about the kind of mental atrophy that takes place when you are relying on these tools so much. And people have been talking about that for a long time, but they have kind of been right. It's just that there's still been a lot of, like, people used to say this about search engines, about reading and writing. I think it was the Greeks. Anyway, a bunch of important Greek people basically had the idea. I think it might have even been one of the bigs, like Plato, Aristotle, maybe was had some notion that the written language would cause the ability of people to memorize to atrophy. And so it was an evil thing. It was a bad thing. People should not write things down because then people would forget how to remember. And we laugh about it. We could laugh about it now, but he was right. People used to remember like whole poems and stuff. People used to like just memorize all kinds of stuff. Not everyone, obviously, but like intellectuals used to remember a lot of stuff. And now we don't really need to in the same way. A lot of that practice went away. And the same is true probably of search engines as well, to some extent. So they were right. It's just that it didn't matter because there was still so much intellectually useful labor to be done that would keep us sharp. And I don't know, maybe we're reaching a point at which a certain amount of work and activity is becoming a bit mindless. And so we do need to worry about the atrophy of our skills and our, if we spend all our time talking to AIs, then an atrophy of something. Socrates probably. Yeah, Socrates probably didn't write. That sounds right. Harmony High Pass, what program are you using to write math? This is Excalidraw. It's just a whiteboard piece of software. Other whiteboards are available, TL Draw. And I have a bunch of shortcuts that give me the symbols, or I copy paste them from somewhere. It's not very good, but yeah. So I wonder if there's going to be a kind of much more of a people needing like intellectual to have an intellectual gym of some kind which I think in a way could be really good. Like it could be a nice thing for us. What would the intellectual gym for adults look like? What would we want that to look like? Could be great. Oh no. One thing I would remove from the intellectual gym is all of these word puzzles. Everything is funny so as long as it is happening to somebody else. Everything is funny. It's like a for all there. Everything. Let's go. I guess we have X, X being the set of everything. As long as is like a, it's like an if then maybe. So it's like a, P and a Q. Miku thinks it's a if and only if. That's an interesting idea. Everything is happening to somebody else as long as it is funny. No, that's not quite right, is it? Everything is funny. So the idea is funny. Everything is happening to somebody else as long as it is. Yeah, I'm struggling to reverse that and have it make sense. Yeah, Excalibur is pretty cool. Excalibur is pretty cool. It's not brilliant for maths, but it's getting me this far. If and only if. Yeah, maybe you're right. Maybe it is if and only if. Well, how many answers? How do I check answers? Well, at the moment I'm only doing the odd ones, and there are answers at the back for the odd questions. If it was a more, I mean, it's kind of challenging, but it's also kind of boring. So I'm skipping the even ones mostly. So let's see. Yeah, that's Miku's point. Miku's point. As long as seems to be equivalent to if and only if, but it's one of the it's not really formalizable. Okay, 2.9. Let's find out what the sage and theorist Richard Hammock says about this statement. And let's see if I can manage to mark any of these. Okay. Well, that seems correct. Great. 3, yeah. Yeah, okay. I think I'm just saying the same thing. 5. Oh. Okay, 5. Did I get this anywhere near right? Okay. For all epsilon in rational numbers, sorry, the real numbers, where it's greater than 0, there exists a delta, again in this similar situation, and then we've got this, if this, then this. Oh, amazing, I got that one right. Okay, 7, there exists a real number a, for which, yeah, okay. If for e, there exists a in the real numbers for all x in the real numbers. Okay, both of those are right. 8 is not given an answer. 9, this and this and this. Okay, great. Okay, 11. There is a providence that protects idiots, drunkards, children, and the United States of America. One translation is as follows. Let R be the union of the set of idiot... Yeah, the union is probably the right thing. Idiots that are drunkards that are children, and the set consisting of the USA. Let P be the open sentence PX. X is a providence. That's pretty much the same. Let S be the open sentence. Oh, no, wait, it's not. He's broken it up. He's broken it up. He's broken it down a bit deeper than I have. He's broken this up. So we've got... Oh, other way. There exists... I guess I did have that wrong. So I was saying for all the items in this set, there exists a providence that protects them. He's saying there exists a providence. So I guess the statement implies that there is a single providence that protects all of these things. And my statement really implies that there is a providence that protects each one, but it doesn't say anything about them being the same providence. So mark it 0. Nope, wrong. 13. Okay, let's see what it says for this. Everything is funny as long as it's happening to somebody else. Translation. Well, I got this part right. And then he's saying he's got X is happening to me. Oh, so he's translated this else. So instead of... Yeah, so he's used the if then, not the if and only if. That's interesting. And he's saying he's broken down X is happening to somebody else as X is not happening to me, and X is happening to somebody. So he's broken that down a bit deeper than I did. And he's saying if these things are true, then it's funny. So it's not what do they call it? Reversible? Buy something. Well, okay, that's the solutions. Where are we at? Yeah, I mean, he's got a point there, but also it's a kind of a silly exercise. Biconditional statement. It's not a biconditional statement. Which I suppose makes sense, really. Like, it isn't really, in reality, a biconditional statement, is it? Everything is happening to somebody else, if it is funny, would be the biconditional version of that, and that's not true. Well, that was thrilling. Really hoping for no more word questions. Okay. All right, we got this chapter, and then we got, that's it. Okay. Given a statement R, it's negating statements. Given a statement R, the statement tilde R is called the negation of R. We know that. You already covered that ages ago. If R is a complex statement, then it is often the case that the negation of R can be written in a simpler or more useful form. This process of finding this form is called negating R. Oh, okay, so it's like an operation. In proving theorems, it's often necessary to negate certain statements. We will now investigate how to do this. We've already examined part of this topic, De Morgan's laws. That's these ones. From section 2.6, can be viewed as rules that tell us how to negate the statements P and Q and P or Q. Whoever said in the chat earlier about this being like an A for and. Real, yeah, thank you. That's been very useful. Here are some examples that illustrate how De Morgan's laws are used to negate something involving and or. Example 210. Consider negating the following statement. You can solve it by factoring or with the quadratic formula. So if we were to negate this in everyday logic, you can neither solve it by factoring nor with the quadratic formula. Or maybe that's not quite right. Well, anyway, let's read on. Now, R means you can solve it by factoring. Yeah. Which we'll denote as P, Q. The negation of this is negation P or Q equals the negation of P and the negation of Q. Therefore, in words, the negation of R is you can't solve it by factoring and you can't solve it by the quadratic formula. Okay, so I had it roughly right. Maybe you can find negation of R without invoking De Morgan's laws. That is good. You've internalized De Morgan's laws and are using them unconsciously. Oh, great. Oh, wonderful. We will negate the following sentence. The numbers x and y are both odd. The statement means x is odd. Yeah. Let's move on to a slightly different kind of problem. It's often necessary to find the negations of quantified statements. So this is what our one regular was saying earlier. It's really Ren, I think. Yeah, it's really Ren was saying earlier. Okay. For example, consider the negation of this. Reading this in words, we have the following. It is not the case that Px is true for all natural numbers x. This means that Px is false for at least one x. In symbols, there exists an x in the set of natural numbers where the negation of Px is true. Thus, Similarly, you can reason out that the negation of a there exists is the for all of the negation of the statement. Fine. We've got some laws. Be sure that you understand these two logical equivalences. They conform to our everyday use of language, but they pin down the meaning in a mathematically precise way. Consider negating the following statement. The square of every real number is non-negative. Symbolically, R can be expressed as for all x in the real numbers, x squared is greater than or equal to 0, and thus its negation is same statement again, negated. There exists an x in the real numbers. No, wait. There exists an x in the real numbers where this is not true. X squared is greater than or equal to 0. Oh yeah, because we're negating it. Yeah. So it's like find a counterexample. And then they flip the comparison. In words, this exists a real number whose square is negative. Fine. Observe that R is true and negate R is false. Maybe you can get negate R immediately without using equation 2.8 as above. If so, that is good. If not, you should be there soon. Okay. If a statement has multiple quantifiers, negating it involves several iterations of equations 2, 8, and 2, 9. Consider the following. For every real number x, there is a real number y for which y cubed is x. This statement asserts that any real number x has a cube root y, so it's true. Symbolically, s can be expressed like this. For all x's in the real numbers, there exists a y in the real numbers for which the cube of y is equal to x. Okay. Now if we want to negate this, we can say there exists an x in the real numbers where this statement here is not true, and the statement in question is there exists a y in the real numbers where y cubed is equal to x, and then we negate this one as well, which means we get this, and then we negate that like that. Okay. Thus the negation is a false statement that can be written in either of the following ways. There is a real number. In writing proofs, you'll occasionally have to negate a conditional statement P implies Q. The remainder of this section describes how to do this. To begin, look at the expression negate P implies Q, which literally says P implies Q is false. You know from the truth table for if then that the only way that P implies Q can be false is if P is true and Q is false. Therefore, this, yeah, we did. We've got some examples. Are these interesting at all? I don't think so. If x is odd, then x squared is odd. We want to negate that. Or rather, we put it like this first, then we negate it, and we need to break this down bit by bit. Okay. This seems like it will be fairly challenging. Translating back into words, we have there is an odd integer x whose square is not odd. Notice that r is true and negation of r is false. Hello, Nime, how you doing? I've seen you around, I think. I saw you on Hoyland's chat, Stian Hoyland's chat. Good to see you. Okay, the above example, etc., etc. This type of problem can sometimes be embedded in a more complex negation. See exercise 5 below and its solution. Okay, we're doing negating again. We're doing this statement again at some point. Very exciting. Okay. Right. I'm going to take a short break. And I'm going to be back. We're going to finish off this chapter of the logic. We turn up the birds. I think there's some music. Anyway, see you in a minute. We're back. Time to negate. Or is it not time to negate? Is it ever the time to negate? The answer is no. It's time to negate. Okay. The number x is positive, but the number y is not positive. So if we were to put this in symbols, we could say x is greater than 0. And y is well, we could put it like this. If we want to negate this, then we would do something like initially like this, and then we need to work out I think the negation of the group by, I think it's De Morgan's laws, means that we want to negate each one and then flip this to an OR, and then we negate this one, which gives us this. And then I guess if we negate this, we're ending up with this, I think. So I think we end up with that, which means x is not positive or y is positive. Kind of a neat trick doing this, because it is kind of hard to reason through in your head. Two, if x is prime, then root x is not a rational number. We did all these already. Let's not do the even ones again. Okay, 3. For every prime number p, there is another prime number. Oh wait, he's mixed them up. He's mixed them up. Okay, for every prime number p, we want this a here. For every prime number p in the primes, there exists as the backwards e. There exists another prime number where q is greater than p. So that's the true version. If we want to negate this, then we have to negate the for all. And the rule here is we change this to this, and then we negate what's inside. We negate what's inside here. And then to work this out, we change this to a for all, and we negate what's inside here. And to do this, we do that. And so we say, to put this in a sentence, there exists a prime number p where all prime numbers for which every prime q satisfies q is less than or equal to p. So there exists a prime p for which every prime q is less than p. So this is what a funny negation. Can that be true? So this one's saying for every prime number p, there is another prime number q where q is greater than p. So for every prime number, there's another one that's bigger than it. And we're saying here, the negation is there exists a prime p for which every prime q is less than or equal to it. Doesn't sound right. For every prime number p, all right, let's do this. Let's work this through again just to make sure I'm not making a mistake here. Okay, so we're negating the whole thing. We're saying for every prime p, there exists a prime q where q is greater than p. Okay, fine. We want to negate this. We change this to we follow this formula, right? Where's the formula? Yeah, we flip this and we negate this. That looks right. Then we keep this, we negate this, and this gives us an all. And we negate this. Maybe it is right. Kind of funny if it's right. I mean, it's a negation, so it doesn't have to be true, I guess. In fact, it probably has to be false, but anyway, we'll find out. For every positive number epsilon, all right, we've done this. We've done this one already. We don't have to do this one again. What was it? This one, wasn't it? So we want to negate this now. So to negate this, we change this to an every. And then we negate. Actually, maybe we phrased this wrong in the last one. It's going to make negation a bit difficult. Yeah, we need to have this. And then this. And then this, and then this, and then this. This is going to be horrible. It's going to be truly horrible. Okay. So let's say if we've got this now. Right, so we need to negate this. And we want to have... I guess this is an implicit and probably. Yeah, so we've got that. Then to negate this, we need to have, we negate this, flip this to this, negate that. And then we do this. And then we flip this. Yeah, we flip that. And this is going to be implicit, and so we're going to flip it to an OR. We flip this one around. And then we have the negation of this. Right, negation of that. Negation of the... do we have a negation of this somewhere? Is there a law or something? No, we get to work that out. These are equivalent, not negations. So what's the negation of a if then? I feel like maybe this was mentioned somewhere. Yeah, no, that's not there. Ah, here it is. Okay. So we then get, out of this, we get P or, no, and the negation of this. And then, can we just flip this for negation? I feel like maybe. Alright, that's what we got. Looks awful, but who knows? 7. I don't eat anything that has a face. So we can say no. I don't eat anything that has a face. Now, if we were trying to negate that, just as a human, say the opposite statement. Maybe I eat something that has a face. Maybe that. Nine. If sine x is less than 0, then it is not the case that 0 is, so x is between 0 and pi. Okay, so if we want to negate this, then what's that identity again? That's it's sin x less than 0 and it's like an, what is it again? Is it and or? Take a guess. And and the complement of well, I've already got the complement there, so I can just take it out. Okay. That seems like a nice easy complement. A negation, sorry. Really want to have it be complement. Okay, you can fool all the people all the time. Yeah. So I wondered about that. I don't eat anything that has a face as a negation. Is it I only eat things that have a face? So I think this has to cover, I think this negation has to cover all the situations in which this is not true. So if I ate 5 things that had a face, then this would not be true. So it should be captured in the negation of it, I think. So I think it's I mean, we will find out. We'll find out what the intended answer is. So if you can fool all the people all of the time, let's say there exists a person who you cannot fool at least some of the time. Maybe. All right, that's enough time in the logic minds. Let's find out. Let's find out what Richard Hammack's answers are. All right. Now, where were we? The number x is not positive or the number y is positive. Okay, that's right. 3. There is a prime number p such that for every other prime number q, q is less than or equal to p. Also, there exists a prime number p for which... Is this? Yeah. Oh, I actually got that right. IceLemon0 asks, what software do I use to write proofs and notes? So I'm just using something called Excalidraw at the moment. It's like an online whiteboarding software. Other online whiteboarding software is available, like TLDraw, for example. It's not necessarily brilliant for mathematics, but it's decent if you are trying to display at the same time, and you're not going to try and get in the LaTeX minds. But try. I mean, software like this is useful for all kinds of things as well. So, Excalidraw or TLDraw, all pretty useful to know. Okay, the negation of this, which I have no idea how you write it in words, is okay. Right, so we've got every epsilon, no, if there exists an epsilon, the real numbers in the interval, I reversed I included the interval in this, and I think that was a mistake. Yeah, that was wrong. I did think that was a little odd. Yeah, I don't think anyone does use Excalidraw for this. There is an Obsidian plugin that has maths stuff built into Excalidraw, which could be worth looking at if you like that workflow. If you like Excalidraw. Is this a rigorous proof for limits? I'm not attempting to rigorously prove anything to do with limits, but I understand that that is what this particular statement is about. Though my focus is on, so this particular chapter we're working through is on logic. So we're looking at negating statements. What the statements mean is not necessarily important for this particular exercise, but this one in particular, I don't know, because I believe it's something to do with calculus, but my calculus is quite a way out of date. Okay, then I mean, this is just miles away. It's miles away. Oh, dogs. Dogs are barking. Okay, A. Well, some parts of it were right. Not good. Okay, 7. I'll eat something. I eat something that has a face. Okay, yeah, I'll take that. Note if your answer was I will eat anything that has a face, then that is wrong, both morally and mathematically. I'm sorry, Namir. You're being. He's talking trash about you in the answers. There exists a number x for which sine x and yeah, fine. And then 11. You can fool all of the people all of the time. There is a person, yeah, there exists a person who you cannot fool at least some other time. Okay, I'll take that. Real analysis, yeah, that could be it. Yeah, I mean, this was quite a lot. There's a bunch of rules I don't know there. I think one thing I just need to label as a thing I don't quite get yet is if you have if you have like a sequence of commaed statements, how they get negated. So let's say if this is negated here. So using the intervals was a nice thing. The intervals saved a bit of work there. If you have a set of negations, like I don't know how that works. So we've got, let's say our statement is this. And these are separated by commas. So we've got the thing saying what it's within. We've got this, there exists, and we've got this. And when we're negating, the way he's doing this is he's negating the whole thing. Then he's swapping this over from a for all to a there exists, and negating all of this. So this gets grouped with that. Then he's swapping that over. The interval stays as it is, which, because I did that weirdly the first time around, that tripped me up. And then he negates this. And then he uses that formula we looked at earlier to negate the implies that operation. Whoa, okay, yeah, that happened last time. I don't know why it cuts to like wild rainfall there. Sorry. Rain out of nowhere. Okay, so we get that. Yeah, so that was one thing I didn't quite get. But it looks like you just roll along. And then it looks like putting this, the right choice is to put this in a single set or something like that. So I just need to mark this a little bit suspect. I need to be careful if I work on anything like that again. I don't think I'm like missing huge knowledge there, but I definitely am missing some skill. Still, it might not massively matter with what I'm trying to do, but I should just mark that as something I need to be careful about. Okay. Where were we at? Okay, 210. Now we are almost done on this chapter. 2.11, logical inference. Suppose we know that a conditional statement PQ, let me get rid of these. Suppose we know that a conditional statement P implies Q is true. This tells us that whenever P is true, Q will also be true. By itself, P implies Q being true does not tell us that either P or Q is true. They could both be false, or P could be false and Q true. But if in addition we happen to know that P is true, then Q must be true. This is called a logical inference. From two true statements, we infer that a third statement is true. In essence, statements P implies Q and P are added together to get Q. We can indicate this by stacking P implies Q and P one atop the other with a line separating them from Q. The intended meaning is that P implies Q combined with P produces Q. This is a very frequently used pattern of thought. In fact, it is exactly the pattern we used in the example on page 34. This rule even has a name. It is called the modus ponens. Now, that is... I'm going to have to look up how to pronounce that. Wow, okay. Modus ponens. Modus ponens. Modus ponens. It's called the modus ponens rule. Two other logical inferences, called the modus tollens and elimination, are listed below. In each case, you should convince yourself, based on your knowledge of the relevant truth tables, that the truth of these statements, of the statements above the line, forces the statement below the line to be true. Okay, so this is modus ponens. P implies Q and P equals Q. Modus tollens, P implies Q, not Q, not P. This one is always getting me. Okay, P implies Q, not Q, P. And elimination. P or Q, not P, Q. Fine. Nemo says that elimination is an adopted child. Is it? I guess it is. It does look a little different. It is important to internalize these rules. You already use at least modus ponens and elimination in daily life anyway, but you need not remember their names. Few mathematicians can recall the names that they that they use the rules constantly. These names are not important, but the rules are. I'm gonna look at the truth table for this. Okay, so if we have this truth table for the implies operation, now if we have, let's make ourselves a little marker here. If we say P is true, which is the case here, no, wait. We're saying, if we're saying this is true, and yeah, so we're taking each of these as true, and we're also saying P is true, then we have to be in this row, which would be great if that was, yeah, there we go. We have to be in this row. So Q must be true. Okay, that's good. Now, if we have, if we say that this then is true again, so we're saying this is true, and we're saying Q is false, so we're in this line, then P is true. It's not the only no, wait. No, not Q, not Q, not Q, not Q. Negate Q. That could be this, or it could be this. Yeah, okay. That could be this, or it could be this. The only overlap is here, so we can tell that P is not true. Yeah, the bottom line. Yeah, so when we can say P implies Q is true and Q is false, then we know that P is also false. Because in the only other case where P implies, where Q is false, P implies Q is false. So it's kind of a funny thing, modus tollens. I mean, it is true. It does hold, but it's unusual. Feels unusual. Okay, names are not important, but the rules are. 3 additional logical inferences are listed below. The first states the obvious fact that if P and Q are both true, so is the statement P and Q. On the other hand, P and Q being true forces P, also Q, to be true. Finally, if P is true, then P or Q must be true no matter what statement Q is. These inferences are so intuitively obvious that they scarcely need to be mentioned. However, they represent certain patterns of reasoning that we will frequently apply to the sentences and proofs, so we should be cognizant of the fact that we are using them. An important note. It is important to be aware of the reasons we study logic. There are 3 very significant reasons. First, the truth tables we study tell us the exact meanings of the words such as and, or, not, and so on. For instance, whenever we use or read the if-then construction in a mathematical in a mathematical context, logic tells us exactly what is meant. Second, the rules of inference provide a system in which we can produce new information or statements from known information. Finally, logical rules such as De Morgan's laws help us correctly change certain statements into potentially more useful statements with the same meaning. Thus, logic helps us understand the meanings of statements, and it also produces new meaningful statements. Logic is the glue that holds strings of statements together and pins down the exact meaning of certain key phrases such as the if-then or for-all constructions. Logic is the common language that all mathematicians use, so we must have a firm grip on it in order to write and understand mathematics. But despite its fundamental role, logic's place is in the background of what we do, not in the forefront. From here on, the beautiful symbols and, or, implies, if and only if, negation, for all, and there exists are rarely written, but we are aware of their meanings constantly. When reading or writing a sentence involving mathematics, we pass it with these symbols either mentally or on scratch paper so as to understand the true and unambiguous meaning. Oh, glad we got through that. Just have to do this all the time for all of the rest of the work I do with proofs forever. But hopefully it will fade into the background of my mind at some point. Now, the chapter 3, which is the last, I believe, non-proofs chapter. Let me just verify this. Yes, finally, then we will be done with the prerequisites to the prerequisites to the prerequisites. We will be able to look at some proofs and begin maybe to interpret the basics of what proving is about. And at some point get into everything else. Now let's just for my own amusement, going to look at what we're looking at when it comes to counting. Because I think, again, I may know a bit about counting already. It may seem peculiar that a college... I don't need to read it. I'm just spooling through it. Why am I reading it? Okay, lists. Lists. Yeah. Yeah. Dice. We've got some dice. Yeah, I've done this before. Yeah. Yeah. Why do I feel like he's going to force us to write out like 100,000 items? He's be like, please write out the permutations of a 10-item list in full. Yeah. There's going to be. I know there's going to be some of that. All right. Good. Yeah. Okay. Yeah. Yeah, permutations. Yeah. Oh, wow, we got quite a few exercises there. I'm definitely going to use programming for this. Counting subsets, fine. Pascal's triangle, binomials, binomial theorem, whatever that is. Multi-sets. Who knows? Bunch of stuff. Pigeonhole principle. I like the look of that. And then it goes on. Just all of that to do. All right. Well, I should hopefully be able to skim through that a little bit as well. and then we'll be on to proving, and then we'll be able to take another look at the programming book. Please write out the permutations of the playing deck. Yeah, I do feel like he might ask us to do that. Okay. All right, that's me done for the day. Let's see who's on, who we can go hang out with. Who have we got? I've been spending a lot of time on DevGirl streams lately. It's French. I don't understand French, but the vibes are incredible. I have no idea what's going on, but it's great. Would recommend checking out. But of course, she's not online right now. Okay, what's happening? Game dev as always. Nothing against game dev. Love to play games. Somebody's playing Go. That's kind of interesting. Somebody is... we've got a couple options. Got a couple. Just refresh for me. All right. We're going to go spend some time with Kufi Man. Thanks for hanging out, everyone, and have a good rest of your day to everyone. And I will see you next week, if not before. Probably, maybe before. But if not next week, next Thursday. Same time, same channel. 7, 6, 5, 4, 3, 2, 1, go.